No, I forgot that I logged in first today.
Yeah, okay.
Okay. Yeah. Thanks, Surendra, for reminding. Yeah. So I close that YouTube now.
Yeah, you can close.
Very large group.
We have just hit a, so I think it's just 1 minute.
Okay. Yeah, you've crossed the 100 mark.
Yes. Yeah, it's also time. So good morning, everybody from India, and good evening, Dr. Chris, from United States, California, and I welcome you to this international conference on GeoGebra in India. And I will request you to, Chris, I would request you to say a few words about yourself and you start your presentation. Chris.
Thank you, Inder. I appreciate your kind words and your invitation. Greetings to everyone in India and lands beyond. I'm not sure where all you are from, but I am from California, the central part of California, not the beachy kind of place. I don't live where surfers tend to live. I'm closer to the skiers in the snow mountains nearby. I work at a small private university in Central California called Fresno Pacific University, where I direct the mathematics and STEM education master's degree programs. These are programs designed for teachers of mathematics and teachers of younger students who teach all of the STEM subjects together. I would like to talk today to give a basic primer on using the GeoGebra 3D calculator environment on on the web. So I know my description said you should have a smartphone or a tablet to use the augmented reality. But Dr. Reddy, who's giving a talk this afternoon, will also be focusing on the augmented reality application. And I highly recommend that you go see him and see that conversation or his talk. And so my talk will instead try to focus more on the use of the 3D environment itself and how to construct some useful how to construct something of interest, and then use, and along the way I'd like to motivate the use of transformations. My doctoral work, I completed my PhD just a few years ago in mathematics education here in California, and my focus really was on teacher knowledge, specifically around the idea of using transformation geometry to motivate the learning of geometry. I have a colleague, a friend here in the United States, whose name is Tim Brzezinski. He's been working with GeoGebra for many years, and I've stolen this idea from him that there's if transformations are important, they're sometimes more easily understood in 3 dimensions than they are in 2 dimensions. And if you have a means by which you can work towards understanding of various transformations, in this case today, I'm just going to be looking at the single rigid transform called translation. And we will limit our talk to that. Nothing I do. I'm going to build from the ground floor up everything that we do, so you can watch in real time as I develop the solid we're going to look at. And along the way, I hope to reveal a couple of interesting subjects and some possibly some new aspects of GeoGebra. With that labored introduction, let's get started. If you would open up, if you have handy the a web browser, please go to geogebra.org, and you can follow along with me. And I will be trying to do a couple of things. I want to point out a few things right now. Here on the screen's left is a picture from, this is my my iPad using the GeoGebra 3D app that you can download to your iPad or your any tablet will do. Your iPhone, your Android phone, any of those will. It's available there. I would like to focus our time though using the web-based version.
Chris, can I just
Yes.
interrupt? Only your face is visible to us. We can't see your tablet or.
Really? Oh, well, let me see if I can fix that.
Yeah.
Yeah, can you please
thank
share
you.
your screen? Yeah.
Probably
Yeah, how's that?
Yeah,
I thought
that's
I
it.
had.
Yes.
I thought I'd just not pressed share. I'm sorry. I had
No, it's
selected
okay.
the right image.
No
Thank
problem.
you for stopping me, and please stop me if there's a burning question.
Yes, yes.
Ah,
No problem.
okay.
Please carry on.
Thank you. Okay, now we're all on the same page. So what I
Yes.
was trying to say is this here is an image that I'm sharing to my iMac from my iPad. It's the tablet using the GeoGebra app that you can download in the App Store. They have versions for Android. They have versions for any number of other all the platforms necessary and available. If you're wondering how I'm also able to stream my iPad onto my iMac, I'm using a software program known as Air Server, which is a free. You can tell it's free. It says trial down here at the bottom. I am on a 30-day trial, but even its paid for version is relatively inexpensive. Oh, you're getting to see all of my TikTok stuff too. That's just a joy. Okay. Perhaps I will stop sharing my iPad and just use my my web browser. So if you would go to geogebra.org, it'll open up to this page. If you have an account and you're logged in, you should see your image up here in the top right. And once you're here, we're going to be in the 3D calculator environment. So right away, if you just click the 3D calculator, it will create this image. Yours may not your axes may not be numbered the same as mine, but it'll generally have the grayed out XY plane, and the Z space will be in the white above and below the gray plane. Generally, in the 3D calculating environment, the red axis is the x-axis, the green axis is the y-axis, and the blue axis is z. And you can plot points anywhere in this environment. You can create graphs. You can use all of the geometry tools that are available. If you click over here, you can see there's quite a large number of tools available, and we will be using some of them. But I would like to start first by plotting a few points. So the first point I would like to plot is the origin. Okay, what is going on? Oh boy. It's quite difficult to type when I keep getting pulled into other parts of the conversation here. So I'm going to plot several points just by using the coordinate axes. and labeling, well, better than that, I will now just choose to create points on the axis that I'd like. So I've now chosen 2 points, A and B. One, A is at the origin, 0, 0, 0, and B is out here on the x-axis at 5, 0, 0. And I would like 2 more points. They will be at 0, 2, 0. And the third point I would like at 5, 2, 0. So I have now constructed a nice little, the corners, the vertices of a rectangle in the XY plane. They are right now they are not making a rectangle, but they are in fact just the vertices. I can then use going here, use the polygon tool in the geometry environment. The polygon tool allows me to surround or use these 4 vertices and create a polygon. And now I have that polygon in that plane, the full rectangle A, B, C, D. I can, I don't want that point. Yeah. What I'd like to do now is I would like to take that polygon and translate it along a vector. And to do that, I need to create a vector. Vectors behave like points or can be defined like a point in GeoGebra. By the way, you'll notice when I switched over here to the algebra side, I have these 4 points that I constructed, but by drawing in the polygon, GeoGebra constructed the segments for me, and it created a polygon which it gave a name of Q1. I will now need a vector. And if I start typing the word vector, it knows what I'm looking for. The vector will move the origin. If you just leave it undefined, it will start at the origin and it will move it along the coordinate axes, the number of units you'd like it to go. So I'm going to move this. I'm going to create this vector 0, 0, 4, which is a vector that moves objects, that translates objects 4 units in the z direction. Now, and you can see that here in the actual plane. Here's the vector. It's this black mark with the arrowhead at the top. It's not a construction object in the same way that the segments are. It's something I can use to translate. Now, I have fortunately for me, I can use the translate by a vector tool in this environment. So if I click on translate by vector, what do I want to translate? I'd like to translate that polygon up to a new plane. The new plane is the plane where x and y are held at 0, but it's now it's the z equals 4 plane. I have moved that polygon up to that point. What did not go with it are the vertices, so I can move those without much trouble by clicking on them and migrating them up to and enclosing that second rectangle that's now in space, in the z space at the place where z equals 4. And then I would like to complete the actual polygon. I'm missing the 4 sides. I'm sorry, I want to complete the prism, the rectangular prism. So to do that, I'm going to construct those 4 polygons using the same polygon tool that I used before up here. But before I do that, I'd like to hide this vector. And so I'm not going to need the vector for a little bit. So that black arrowhead kind of gets in my way and is a little distracting. So I've moved it off the visual field. I've hidden it. I will go back and use that polygon tool and create the polygons that make up my lateral faces of the rectangular prism. Remembering that even though the edges may look like they're there, I have to complete the polygon by making a full circle, as it were, around the 4 vertices. I needed to move the polygon. Needed to move the plane so I could see everything, and that's perfectly legal. It's acceptable. I just grabbed the gray plane and drag it. Every time I want to do that, I click on this move button that's down here in the bottom left, and that allows me to stop having the tool, the polygon tool, and instead drag things around as though I were in charge of the universe and able to make things move around the way I'd like. And so now I have created, quite simply, through the use of a simple transform, the translation of one polygon along a vector in the z direction. I've translated that and created a solid that is now of a fixed volume. It's a fixed height. I have done that by creating a whole collection of things. If you go back over here to the algebra side, some of this is all of the code. All of the things that I did are actually GeoGebra algebra commands that I can make use of. And I could have typed all of what I did by pointing and clicking, typed in these things and created them myself. I could have named all of these segments and drawn them all in. I could have created these extra polygons and made those visible as well. I don't. When GeoGebra is originally started in the 3D world, there's the construction, the order in which you construct things is how this column is organized. But you can change that by going to settings over here and clicking on settings again. And in this funny little algebra, this is the algebra symbol universally in the graphing calculator is the default symbol for the algebra environment, and that's talking about this piece over here. If you click on that little cubic looking curve, you can tell tell GeoGebra not to order things through construction order, but instead you can group things by object type. You can have them collected based on dependency, and we're not going to use anything with the layering at this point. I'd like to see things in object type, so that when I want to, I can go over here and I can see. Let's see what there are segments, and here are all the segments that have been created in the last 22 minutes. Here are all the quadrilaterals I created in these 20 minutes. And here are the points I've created in these 20 minutes. You can see I made point A, point B, point C, and point D. I defined them, and then A prime, B prime, C prime, and D prime are translations of their respective pre-images, A being the pre-image of A prime being the image of A under the translation of A by vector U. This little U here is this vector that I defined down at the bottom. Now, I'm going to I can change a few things with this vector, though. It's not fixed. That vector is not a once I type it, U is the name of the vector, but the arguments of the vector don't have to remain the same. So I can go through here, and if I'd like, make this a shorter prism. By now, I've changed that vector from translating everything 4 units in the z direction to just translating them 2 units in the z direction. I can also, if I want, make them go 5 units in the z direction. But I wonder, so that's a rectangular prism. I wonder what happens if I change the vector. So this is the thing that I've always loved about GeoGebra. It's and one of its cousins, Geometry Sketchpad, and also things like spreadsheets and so on. These are worlds to explore. These are places where students and teachers can come together and ask questions. I wonder what would happen if. And I wonder what would happen if I took that middle 0 and made it something else. Maybe I make it a 2. Again. And when I do, I no longer have I have something different. Something else has changed. It's no longer a right rectangular prism. It's still a rectangular prism, but now it's kind of crooked. If I want to get a full view, I can send this thing to spinning around and sort of look at it from many sides. I can look at it from underneath if I want. As if I had the ability to grab this prism and turn it around and touch it and move it and get a sense of what's happening and how it's yes, very useful in mensuration concepts. It's also very interesting if you can work from here to ideas of volumes. You can compare the volumes of this object with its with its initial object. I can change this vector so that the x coordinate or the x value also changes. I wonder if what happens if I type in a negative number here. Can I do that? Well, yes, I can. I can. That's not an impossible thing. What it's done is it's taking everything that was here, the origin, and all of its mappings, right, are being everything that's mapped from the origin goes 3 units in the negative direction on the x-axis, 2 units in the positive direction on the y-axis, and 5 units in the positive direction on the z-axis. GeoGebra Classic. You need the three-dimensional environment. This is which is available for download for free from the GeoGebra website or available in the web version. And also there are apps available for it in your app store. In case you're bothered by the monolithic colors of this, you should know that clicking on the actual polygons allows you to change their colors. I don't like that blue. I'm more of a fan of deeper blue. I don't like how it's lacking any opacity, so I'm going to ramp that up a little bit and give that a nice deep blue there. And then this top one, I really like the top one being more of a yellow color with almost entirely opaque. I don't know why I do, but it does. It makes me happy. Click on something else. And now I can see, going through this, I can see various different yes. You can construct a net for this. There are ways in which you can actually construct the net for solids and animate them in GeoGebra 3D. Speaking of animation, I'd like to do one real quick interesting thing. I'm going to create 3 sliders. I'm going to call them, I'm going to call one slider X shift. I'm sorry that it's way down at the bottom there. And I'm going to start off by saying X shift equals 0. And it's going to disappear. You can't see it right now. But it's not gone. I'm also going to create a Y shift and set it equal to 0. And then I'm going to call Z shift and start off with it equal to 4, just for fun. You'll understand momentarily. Remember when I said that we could organize all of these objects, the constructed objects, not based on the order in which they are constructed, but by object type? Well, what I just created were sliders, which are actually numbers, and number n, the letter n is earlier in the alphabet than P for points or Q for quadrilaterals in the English alphabet. So those things that I created are numbers. They're interesting. Numbers come with these values attached to them. You might have guessed what I plan to do with these things. What I'm going to do is, in case you haven't guessed, is I'm going to go back down here to my vector, and instead of putting in -3, I'm going to put in x shift. And instead of 2, I'm going to put in y shift. And instead of 5, I will put in z shift. And watch what happens when I press enter. Notice you saw something in the actual solid. It went back to that original drawing I made, the original prism, which is oriented with the one vertex at the origin, and then the other vertices in that orientation of being 5 units on the x and 2 units on the y, and then 4 units on the z. Can you sketch a paraboloid? I can sketch a paraboloid. But give me a moment. Let me finish this. But yeah, you can sketch any solid of revolution. So I have just looked at the transformation translation here. You can do rotations about any line in space that you'd like. So if you draw a function, if you draw the function y equals x squared, you can then revolve that around the y-axis if you'd like. It's almost that easy as well. But I just want to finish this one quick little demonstration. Remember, I defined these values x shift, y shift, and z shift. These are literally these are number ranges. The GeoGebra defaults to giving you -5 to +5, and you can come along now and you can shift these variables. And if we could see it, down here at you see the vector, that 2.8 that I shifted the x shift to shows up as the actual value in our vector u. And this is the part that I just love. So, and that's this. You can animate this object and let it shear through space in all 3 directions if you want. I don't like shearing. I don't like it necessarily growing in the z direction for this demonstration, but it's perfectly acceptable to do so. But I can shift it into the y. And you can watch how these values, as they pass from positive back to negative, that means the slanting, no longer right rectangular prism is slanting to the negative side of the y-axis. If you could see better, you could probably see it down here at the negative 12. There's an actual negative there. Up here at the positive 12, there's no negative. And again, this is the y-axis, what we're usually thinking of as the vertical axis in a two-dimensional plane. You get that design. Okay. And we can shrink and change this z in all sorts of ways, including take it beneath the plane. And again, I am just grabbing the gray plane and dragging this thing around. All of this is infinitely malleable to you as the user. You can, if you prefer not to have the plane, that gray plane show up, you can go to settings and unshow that plane. You can also hide the axes, and then you've just got this fun little object that's wiggling around in space. And if you press play on all three of the shifters. Now, one of the things that I want to be, I love to make sure that my students get hold of is what's being translated and what's being fixed. What isn't being translated? What things are constant? What are the invariants of this transformation? Well, the invariants are the endpoints. You know, what endpoints form which segments, but also the actual area of the original polygon is unchanged, and the area of its image is also unchanged. So let me put this back. And I think I'm Inder, am I out of time?
Well, if you want to take 5 minutes, that's nice.
Oh, yes, I would happily take 5 minutes. I would take questions for a little bit of time.
Want to say something more? Please go ahead. Then we'll take questions after that.
Oh, okay. A few more minutes?
Yes. Yeah,
sure. Someone did ask for a paraboloid. I'm going to create a new drawing for that. I could just clear all of this out and start over. But what I think I will do is I'll go back here to the 3D calculator and generate the 3D calculator, an all new construction area. And then I will type the function, we'll call it g of x equals x squared. Yes? And then what I'd like to do is I'd like to rotate. So the beautiful thing about this is it will tell you what object and what angle would you, it tells you what you'd like to ask you, what would you like to rotate? And I would like to, and it tells you what are the things you need to you want to put in here. So I'm going to type, I need an object, so rotate g of x. I'm sorry. I'm going to rotate the object itself. It doesn't. Oh, I need to give that a better name. Yeah, what do I want? Y equals x squared? Yeah, so y equals x squared allows us to get that whole, that gives us, the beauty of that is, oops, where'd it go? Gives us everything in the z-axis as well, with z being wait, don't do this to me. Yeah, g colon equals rats. I'm sorry, I've just made a mistake, and
Yeah, I
this
think
isn't going good.
it's okay.
There
Probably,
you go.
yeah, it comes on something.
Yeah, I keep getting, as I'm typing I get interrupted through the Zoom meeting. So
That's right.
I'm sorry. Okay.
Yeah, I
Let me.
think it's sometimes the bandwidth is slow somewhere, and then there is a
Yes.
fine.
I've run into some bandwidth issues, so I'll just stick with where I was and with what I was prepared to talk about, and that we'll stop with that.
Right, nice of you.
Thanks.
I think we have 5 minutes for question answers in case somebody would like
Yes.
to ask questions, doubts, clarifications, suggestions. Please,
Yeah.
Soumya and Makran, please keep a tab on if somebody wants to say something.
Yeah, if someone has any question, they can raise hand or unmute.
Please say your name and then ask the question. Yeah.
You can save this. I can save this construction. I don't know that you can export an image of this, and it'll be downloaded. But I don't believe it's a PDF. I think it will download as a JPEG file
Yeah,
or a PNG, and that'll get you just this picture, the last picture that you're looking at. You can also, the nice thing is you can copy this to a clipboard and paste it into another document as an image.
That's similar to 2D graphics view, right? Where you can save as export as JPG and paste it somewhere.
Yes.
Yeah, fine.
Yes.
So 3D also is possible.
Correct.
Anybody has a question to ask?
Yes, someone's asking about the cone, cylinder, and sphere. Yes, you can, for instance, to construct a cylinder, the easiest way to construct a cylinder is to locate a circle in the plane and translate the circle in the z direction using a vector, and then wrap it as well. So
yeah, I think that will be interesting to generate a cylinder in two different ways. One is by translation and other is by rotation.
Yes.
That will be an interesting task for the students.
Right. You can create a cylinder by rotating a rectangle about an axis. what is U? Use the name of the vector that I chose.
Hello.
Yeah, so last
Hello.
question, please.
Hello.
Say your name. अपना नाम बोलिए और please say your name and ask the question.
Sanjay Basme from Solapur. Hello, sir.
Yes, go ahead.
Hello.
Ask the question.
It is used for the cylinders or cones with the help of 3D picturing. Any demo
I'm
is
sorry.
available?
I think what you should do, I'm answering for you, Chris.
Thank you.
You should go to GeoGebra org, surfaces of revolution, and all 3D objects, how to create them are available in the applet format in GeoGebra org. So you can download it from there. So that is not a problem.
Okay, thank you, sir.
So I think we are just running out short of time. So you can always send questions to Chris. Can you write your email in the chat box so that
I can.
I reach out to you?
Hello, sir.
Just a minute. So you will find his email ID in the chat box, or we'll also do it later on, combined thing.
There it is.
Yeah. So chris.brownwell.fresenco. I'm sorry. I think you better read it yourself and copy and save it instead of me reading.
Chris, yes.
It is there in the chat box.
Brownell at Fresno. Yes.
Yeah. Pratap, you wanted to ask something?
Yes, sir. Hello, sir.
Yes, quickly ask your question. We can hear you. Ask question.
Sir, we can connect the 3D GeoGebra with AutoCAD for 3D designing of home.
I don't know whether Chris would like to say whether AutoCAD and GeoGebra are in any way compatible or connectable.
I'm not sure what software you're referring. Is that a software package? I'm not.
Yes, CAD is a software computer.
CAD. I'm sorry.
CAD,
I misunderstood.
Yeah.
Yes, you can. I know that you can. If you're hoping to export this into something that you could, for instance, turn into a 3D printed object, you can export these files into .stl files, which can then be used. Then you can edit those STL files in. I know you can edit them in Adobe Dimension, so I would assume that that's a fairly. You could use it in CAD as well.
So I think let me close the session by thanking Chris for the short, sweet, and very accessible talk. Because I know 3D is something which all teachers and students normally are a bit scared of to touch. But I think you have motivated enough. You have given the fire for the teachers to start learning 3D and using it. And you touched a very important topic in advanced mathematics called linear algebra, where transformations are very important. So this is the beginning of the topic called linear algebra for the school level. Thank you very much, Chris. Thank you very much for taking time and having your dinner very fast and then coming over on the platform.
Thank you. You didn't rush my dinner. I appreciate it very much. I want to point out on GeoGebra, the GeoGebra website, there are many tutorials about how to do what it is I did. Many of them much more easily understood than mine and that go much further than what mine did. But I highly recommend them. And I will just stop with that.
Thank you.
Except one last time to say, I want to say two more things, if I may.
Yeah,
And
sure.
one is, I highly recommend visiting Dr. Reddy's talk about augmented reality, because he will go further with what you can do to take these images that you construct in the 3D calculator and bring them into the real world, and impose them on objects in the real world and test your construction. And two, I really want to advocate the idea of using transformations in 3 dimensions as a starting ground rather than something you save for later. They are easier to visualize sometimes for students. I
Sure.
recommend it.
Yeah, I think I fully agree with you, because 3D is around us and you can connect with the real world transformation. I surely agree with you. So thank you once again, and virtually thank you.
Thank you. Thank you.
Yeah. Okay.
Be well.
Yeah, and take care. So we end first lecture at this note, and we'll be starting at soon at 11 o'clock, in about 5 minutes. The next presentation by Dr. Ramanujan. So stay connected. If you want to do some ingoing and outgoing, then please do that fast and come back. Thank you. So we'll be back by 11 o'clock. Hello, Ramanujan.
Hello, sir.
Would you like to introduce yourself before I play the video?
I will introduce myself.
Just a short introduction about yourself. Would you like to say something?
Yes, sir. Yes.
Yeah.
Okay.
So please say that, and then I will play the video.
Okay.
Yeah.
Good morning, everybody. I am Ramanujam from Kerala. I'm a higher secondary school teacher working in Kerala. And yesterday, in the panel discussion, Srinivasan sir mentioned about a document, an IT-based maths lab manual prepared in Kerala. I am one of the authors of that document, and I am a team member for implementing mathematics lab in Kerala. We have almost done it. Okay, that's all about me. I have a problem with my internet, so I have prepared a presentation video, and I request Rana sir to play it for me. Thank you.
Thank you, Ramanujan.
Okay, sir.
So I'll play the video sent by Ramanujan, that is integrating GeoGebra in the classroom. I hope technology does not disappoint. Yes, I think it's coming.
Sir, the audio is not visible, audible actually clearly.
I think we'll replay the thing. Probably audio is not there.
Yeah, audio is not very, not at all clear actually.
I think maybe that screen sharing, I didn't do it properly. So let me do the screen sharing. Where is screen sharing? I'm sharing my screen. Yeah, I think let me optimize. I didn't do that, Soumya. So
good morning, everybody. Let me thank to the coordinators of IGCI 2021, especially to Professor I.K. Rana for giving me an opportunity to talk in this event. As the title of my presentation indicates, we have successfully integrated GeoGebra in mathematics curriculum. And the latest development in this regard is the implementation of IT-based mathematics lab in higher secondary curriculum. So let me start from this maths lab. The implementation of IT maths lab in higher secondary is a remarkable change in the history of higher secondary mathematics. I think that this is the first of this kind in the country. Almost all the activities included in the lab are based on GeoGebra. We have prepared detailed lab manuals for the students for standard 11 and 12th and detailed handbooks for the teachers. And we have given exclusive training for teachers based on these mathematics lab activities. The lab activities are also considered for evaluation. In the next month, that is April 2021, the first batch of students in this scheme are going to appear for their mass lab examination. So let us have a glance on the structure of the lab manual and the activities included in the manual. A total of 42 labs are included in the lab manual, 17 from the first year and 25 from the second year. Each lab contains 3 to 4 activities. So a total of 150 activities are included in the manual. Students can select a minimum of 8 labs from the first year and 12 from the second year. Some additional activities are also included with some of the labs. These activities leads the students to some mathematical concepts in depth or to some other subjects like physics, music, etc. The additional activities are not mandatory. Students who are interested in these activities can do it. So this is the structure of our lab manual. So now let us go to some examples from this manual. First of all, we may go to lab 0. This lab 0, deals with the basics of GeoGebra. Students familiarize different interfaces, important tools and commands of GeoGebra through this lab. Next is lab 1. Aim of this lab is to get a well understanding of functions, their graphs, domain, range, etc. In the first 2 activities of this lab, they construct a small applet like this. Using this applet, they can find the images of given numbers under different functions. By construction of this applet, they establish geometrically the correspondence of a number and its image under a function. Now, as we can see from the manual, the procedure of the construction is given in the manual. In the third activity, the people do the third activity with the help of a given applet. This applet is named as function machine. Sometimes we compare a function with a machine which gives an output according to the definition of the function for a given input. This activity helps the students to visualize this comparison. By this activity, they get a clear idea about the domain of a function. A small description about the applet is given in the manual. We can see it. About the applet, some switches are given in the applet. So we can see the applet. Here we can see 3 switches are given here. One in green color, blue and in red color. We can operate the machine with the help of these switches. With the help of this green switch, we can on the machine. And this switch is for resetting the machine and this is to off the machine. Okay. This machine stands for a function. In this example, this stands for the function fx equal to x square. We can change the function using this input bar. Okay. So let it be x square and the input here is 3. So we may start from the first. I am going to off the machine. Now 3 is ready here. We can start the machine now. The function is x square, so we can expect 9 as the output. Yes, 9 is coming as the output. We can change the input. Let it be 4. And again we can start the machine. We can expect 16 as the output and 16 is coming. Okay. Now let us change the function. Let us redefine the function as square root of x. Now the input is 4. 4 is coming in and the output will be square root of 4. The output is 2. If we change the input, instead of 4, if we change the input to -4, see the change in the machine. See, if it is 4, we can see a light blinking in green color. If we change 4 to -4, that light turns to red. It is a warning. Okay. If we neglect the warning and proceed again, let us see what happens. See, we get a question mark as the output. What is the reason of this? See the function here, the function is square root of x and the input is -4. We know that for the square root function, negative numbers are not in the domain of these functions. That means this machine, if it is a square root function, it cannot accept a negative number. Okay, so that is the reason of that warning. Again, if we change the function to instead of square root of x, if it is 1 by x and the input is minus 4, we get the reciprocal of minus 4. But if we change the input, here the function is 1 by x, if we change the input as 0, again we get that warning symbol, okay, because 0 is not in the domain of this function. So this applet or this activity help the students to get a clear idea about the domain of functions. An extension of this activity is given in the second year lab manual. It is given in lab 19. This lab deals with composition of functions. We can see that applet. Here we can see two machines. They are arranged in such a way that the output of the first machine is the input of the second one. And in this example, the first machine stands for the function fx equal to x square, and the second machine stands for fx equal to 2x, the doubling function. And the input is 3. Okay, so let us start the machine. 3 is going into the first machine and its output. First machine is a squaring machine, so the output is 9. And the second machine takes that output and gives the double of 9, 18. Okay. If we reverse the functions, say let us define the first function as 2x and the second function as x square. Again, the input is 3. What happens here? 3 is going to the first function. It gets doubled. And the square of 6, that is 36, is the net output. Okay, so this gives a clear idea about the composition of two functions. And from this example, we can see that f composition g is not equal to g composition f. Now let us change the definition of the functions. Let us define the first function as fx equal to x square and the second function as gx equal to root of x. The input is 3. Now 3 is going into the first function. It becomes 9. And the outcome, the net outcome is 3 itself. Here the functions are x square and root x. We know that root x is the inverse of the function x square. So the first function takes that number and gives the output as 9. That 9 is the output of input of the second function, and the second function brings the 9 back to 3. Okay, so using this activity, the students get again a clear picture about the composition of two functions, one of which is the inverse of the other. Okay, so here these functions are x square and root x are inverse of each other, so their composition is the identity function. Okay, this is just an example taken from our maths lab. If we go further, we will meet with a variety of activities. But before that, I have to say a few words about the strong platform on which we built this maths lab. It has a history of more than a decade. In 2007 December, a team of teachers from Kerala attended the TIME conference, TIME 2007, Technology and Innovations in Mathematics Education, held at IIT Mumbai. Professor Rana was a coordinator of that event. From that conference, we heard about GeoGebra for the first time. It was from a session by Dr. Shailesh Shirali. During the period 2007-2010, we had a curriculum revision followed by a textbook revision in Kerala. This revision based on National Curriculum Framework 2005, NCF 2005, and Kerala Curriculum Framework 2007. Both of these documents give more emphasis on the use of ICT in education. And we preferred GeoGebra for mathematics because we know that GeoGebra is a free software, it is dynamic, it is simple, and it is powerful. As the first step, we included GeoGebra based activities in the teacher handbooks. And we gave a lot of trainings based on these activities. And we got a well acceptance for this. Because even before including GeoGebra in the textbooks, we tried to include the dynamism of that software in the textbooks with the help of a series of pictures like that. And some of the teachers were trying to implement this dynamism with the help of some available softwares like drawing geometry like that. So we got the acceptance because of the simplicity of this GeoGebra. The next major step was during the period 2015-2019. We included GeoGebra based activities in the textbooks itself. Before that, we included the activities, GeoGebra based activities, only in the handbooks. And in this period, we included GeoGebra in the textbooks. Let us see an example of this. See, this is a chapter taken from 9th standard textbook. It deals with circle measures. And a funny thing is that even the page numbers of each page are given in the GeoGebra icon. The pictures are screenshots of GeoGebra, and we can see that in the side box, the construction, GeoGebra construction is given in the side box. And we can see this is a QR code. We can scan this QR code and go directly to GeoGebra applets. GeoGebra applets are already uploaded. So like this, we included a lot of GeoGebra activities in the textbook. And by this time, a lot of GeoGebra workshops were conducted for different levels, for primary teachers, for high school teachers, and for higher secondary teachers. So the teachers are confident enough to use this GeoGebra in their classrooms. Information technology is one of the subjects in our curriculum. We have IT textbooks and it includes GeoGebra activities along with some useful tools like GIMP, Python, LibreOffice Calc, etc. So the students can do the activities given the textbooks. They can practice the activities in their IT labs. So this is the platform on which we built our mathematics lab. Now I have to mention a couple of educational agencies under government of Kerala who give an immense support to implement all this. SCRT Kerala. SCRT Kerala provides the academic support for all such missions. It conducted several workshops for the preparation of textbooks, lab manuals and handbooks. KITE, Kerala Infrastructure and Technology for Education. Formerly it is known as IT School. KITE gives immense support in the form of resources as well as infrastructure. By 2019, all the classrooms of secondary and higher secondary were transformed into smart classes, equipped with laptops, projectors and other accessories. High-speed internet has been provided to all schools. A customized version of Ubuntu equipped with a lot of useful, free and open source softwares are prepared and distributed by KITE. Victors, the educational channel is another initiative of KITE. Now this channel has a major role in keeping the students on the track of learning during this pandemic period. It opened a new learning experience before the students. We are giving orientation classes on Maths Lab through this channel. Samagra is an e-resource portal developed by KITE with academic support of SCRT Kerala. This portal contains ICT resources, unit plans, evaluation techniques, etc. of all subjects from standard 1 to 12. Now let us come back to our IT lab manual and have a close look on some more activities given in the manual. Let us consider lab 2. This lab deals with the shifting of graphs, and the students are asked to draw the graph of the function fx equal to x square. So let us draw the graph fx equal to x square. Then they are asked to create a slider A like this. Then draw another function g defined as g equal to fx plus a. Now they can observe the shifting of the graph G according to the values of A, and they can make some conclusions, and then they are asked to change the function fx. Now it is fx, they can change the function to sin x or mod x like that, and they can verify their conclusions. And we know that the shifting is a vertical shift. And in the next activity, they are asked to edit the function gx. Now it is fx plus a. In the second activity, they can edit this function as f of x plus a. They can edit like this. And again, they can observe the shifting of this graph. And in this graph, in this case, the shifting is horizontal. And these are very simple activities given in lab 2. Now let us move to the next lab, lab number 9. In this lab, we are discussing some concepts from conic sections. And the first activity of this lab, we use a given applet. We can see this applet. And this is the applet given. Here we can see some sliders. Using this slider alpha, we can change the semi-vertical angle of the cone like this. And another slider beta is given here. Using this slider, we can tilt the plane. Okay. And the curve of intersection of this cone with the plane is given. We can see the intersecting curve here. We can hide the cone so we can see it clearly. And the same curve is shown in this window. Okay. One more slider is given. Using this slider, we can change the position of the plane. Now, the students are asked to move the slider beta and observe the curve of intersection. And for different values of beta, see, in this case, the curve is a circle. Now it changes to ellipse and so on. And the students are asked to find the relation between this alpha, beta, and the curve formed. Okay. Now, again, the ellipse changes to a parabola at this position. Now it turns to a hyperbola, and now it becomes a pair of straight lines, and like that. This is the first activity given in the manual. And from the second activity onwards, students are asked to create an applet. And from the second activity onwards, we are treating the conic sections as a locus of a point moving in a plane satisfying some given conditions. Okay, so we can go through these activities. So using the instructions given in the manual, they can construct an applet like this. Here we can see 2 points A and B and 2 circles of the same radii. We can change the radius of the circles using this slider A. Okay. Now P and Q are the points of intersections of these circles. Since the circles are of the same radii, the point P is equidistant from A and B. So the path of P, we can change the value of A, or we can animate this slider and we can trace the path of P. And we know that the path of P is the perpendicular bisector of the line segment AB. We can join A and B to form the line segment. Okay. So we start the activity from this one. Now the students are asked to edit the radius of one of the circles so that the sum of distances of the point P from A and B is a constant. Let it be 10. So what should be the radius of the circles? We can keep the radius of one of the circles as A itself, and if the radius of the first circle centered at A is small a, what should be the radius of the circle centered at B? Since the sum of the distances is 10, we can say take it as 10. We can edit the radius of this circle as 10 minus a. So one of the radii is a and the second radius is 10 minus a. So the sum will be 10. Okay. Now we can animate the slider and observe the path of P. We can see that the path of P is nothing but an ellipse. So from this activity, we can derive the condition of an ellipse. It is nothing but the sum of the distances from two given fixed points should be a constant. That is the condition of ellipse. At this stage, naturally a question will arise in the minds of children. What happens if the difference is a constant? And that question leads them to the definition of hyperbola. They can edit the radii accordingly and they can derive the condition on hyperbola. So this kind of activities generates curiosity in minds of children. They ask questions and they try to solve the questions themselves. Now let us discuss some additional activities. Let us discuss an additional activity given in lab 7. Lab 7 deals with trigonometric functions, and in additional activity we discuss the application of trigonometric functions in physics and then in music and so on. We know that we can represent a sound wave in terms of a trigonometric function. And there is a command, play sound command in GeoGebra. Using this command, we can produce a sound of a required frequency. So let us see how can we do it. So with the help of the manual and the handbook, they can create an applet like this. In this applet, I have defined a function. The name of this function is given as SA. We can give any name, F or G or like that. This function is defined as 2 into sine 256 into 2 pi x. We can see it here. So with the help of the command, play sound command, we can produce this sound. We can see a button here named as SA. I will go to the object property of this button, and in the scripting, a command, play sound command is given. Okay, so we can play this sound like this. Now this is a sound having frequency 256 Hertz, because the definition, in this definition, we can see 256 here, definition of the function. Okay, now let us change the frequency of this function. See the change. It becomes more sharp like this. Okay, now let us fix at 256, because 256 is the base note of middle C. Okay, now re is defined in terms of this 256. Another function is defined here, re, and one more function, ga, ma, pa, etc. All the functions are defined in terms of this slider F. This slider F is for changing the frequency. Okay, so we can play the sound like this. These are the notes of the raga Maya Malava Gaula. If you want another raga, say for example Shankaravarnam differ from Maya Malava Gaula only in two notes. Its Rishabha and its Daivada are slightly higher than that of Maya Malava Gaula. So we can edit these functions, the corresponding functions. We can edit this function Ri, and we can edit this function, and we can play the Shankaravarna Raga also, or the notes of Shankaravarna Raga. If you are interested in this, you can go further. You can create an applet like this. This is a piano created in GeoGebra 3D. You can play this piano. For the convenience, we can change the view like this. And all the keys are associated with a function, like in the previous case. So we can play the piano like this. You can play any notes. You can change the frequency using this slider. You can change the tone of the music or tone of the sound using another slider, and you can change the duration of the play using one more slider. Okay. So if the students are interested in music or students are interested in physics, they can do these activities. And these activities are not mandatory. They are optional. Only interested students can do these activities. Now let us discuss one more lab. And in this lab, we integrate some topics, matrices, determinants, and three-dimensional geometry. We know that a linear equation in x, y, and z represents a plane. So the solution of a system of linear equations, say a system of three linear equations in x, y, and z, is nothing but the point of intersection of these planes if they intersect in a single point. But three planes can intersect in a line also. In that case, we get an infinite number of solutions. And there may be cases in which there are no solutions for a system of linear equations. So we can visualize this geometrically. Okay, this applets, an applet is given for this activity, and this applets helps the students to visualize different cases of existence of solution or non-existence of solution. Okay, while solving a system of linear equations in using matrix method, first of all we will write the coefficient matrix. Then we try to make this coefficient matrix to an identity matrix with some matrix row transformations. Okay, at each step the equations will change, and accordingly the planes will also change. Let us see what happens here with the help of this applet. In this applet, we can edit the equations. Here, three equations are given. We can edit, if we want, we can edit these equations. And these numbers represents the coefficient matrix. Okay. If we click, the steps are given here. The steps of solutions are given here. If we click in each step, we can see the corresponding change in the planes. And we are looking for this point. This point is the point of intersection, which represents the solution of the system of equations. Okay, so we can click on each step and we can observe the change in the planes like this. Okay, the planes are changing, but see that even though the planes are changing, the point of intersection is not changing. And at last, on the left side, we get an identity matrix. That means the first row of this matrix represents, it is 1, 0, 0. So it represents x plus 0, y plus 0, z equal to 0.48. 0.48 is the constant, which gives the solution as x equal to 0.48. Since the equation, the corresponding equation of the plane is x plus 0, y plus 0, z. So it is parallel to the coordinate planes. It is nothing but x equal to 0.48. So it is parallel to the yz plane. And the second plane is parallel to the xz plane. And the third plane is parallel to xy plane. And the point of intersection, we can see the point of intersection and we can see the solution here. And if we want, we can edit the equations. Okay. Now let us see some more examples. Now let us edit the equations of these planes. I'm going to edit the equation of the third plane so that it becomes the sum of the equations of the first two planes. Okay, so by clicking here, we can we get some columns in which we can enter the coefficients. So here we can enter 5, 2 plus 3, 5. Here it is minus 1 and 2, 1. Sum is 1. 3 minus 1. 2, and the sum of constants is 7. Okay. So the equation of the third plane is obtained by adding the first two planes. So we know that all the planes are passing through a single line. Okay, or the third plane is passing through the line of intersection of the first two planes, and we know that in this case we have infinitely many solutions. Suppose we edit the constant term of only the constant term of the third plane. Let us see what happens. We can edit it as 2 or like that. Okay. See, the planes are not intersecting in a single point. In this case, the planes are not parallel, but they are not intersecting in a single point. And this is another case in which we have no solution. Okay. So using this activity, students can compare the existence, non-existence, etc. of a system of solutions with the planes. Okay, let me conclude. Again, I remember the catching slogan of Time 2007. Instead of making kids love the math they hate, make the math they would love. Yes, in Kerala, we are trying to make the math that our students would love. Thank you. Thank you all.
Thank you, Ramanujan, for the very nicely done video with lot of information in it. And I'm sure now there will be a lot of questions from the audience because it directly relates with the activity they do daily, teaching and learning of mathematics. And I'm sure this has ignited many hopes that there are ways of motivating students and gives them tools to learn things. So can you switch on your video possibly, and then we'll have some question answer if possible.
Yes, sir. Sure.
Yeah. So Soumya.
Yeah. So
yeah.
Anyone who wants to ask some question or comment, please unmute.
Good morning, sir.
Good morning.
Can you hear me?
Yeah.
Yeah, you have shown this thing for 11th and class 11 and 12.
Yeah.
Is it there for class 9 and 10 as well?
I think
no.
I will ask, is it available for 5, 6, and 7 also? Yeah. Please go ahead.
Madam, all these activities are taken from Maths Lab, lab manual for 11th and 12th. We have not yet prepared it for standard 9 and 10. But so many activities are given in the textbook itself of Kerala state syllabus for 9th, 10th, 8th, like that.
Any other question? In the meantime, can I say, Ramanujan, that you put your email in the chat box and where they can get that present manual download link also?
Sure, sure. I will share the link of that manual under my email.
Yeah. Yeah. In the meantime, anybody else wants to ask a question can raise the hand.
I'm sharing it from another device.
Yeah, no problem.
Any other questions? Yeah, Dr. Ajit Kumar, please.
Hi, good morning to everybody. And first of all, my compliment to Srinivasan for Ramanujam, sorry, for his excellent lecture, and first of all, taking that much initiative in the state of Kerala. I always give example of teachers' activity in Kerala whenever I'm giving lectures in this kind of thing. So first of all, I mean, it's a kind of bottom-up approach. It's not that the state government has forced it on teachers. So once the teachers are interested, they see the value in making the student learn using these tools. I mean, there are enough means and they can implement in the syllabus itself. That's what I just wanted to say. So my compliment to you, actually.
First of all, thank you for your compliment, sir. Teachers are very much interested in it because they are doing it from, I think, for more than 10 years. So they are using it very well in their classrooms. So we get a good response from the teacher community. But surely some resistance are there from a minority of the teachers.
Yeah, that will always be there because it's a natural, I mean, human tendency first to oppose any new initiative.
Yeah.
Any other questions or suggestions, comments from the participants?
Sir, I have a question, sir.
Yeah, please say your name and then.
My name is Firdaus Ahmed. I'm from Srinagar, sir. Sir, I understand and appreciate that GeoGebra can be used as a great illustrating software. Do you know of any example where GeoGebra can be used to prove something, to prove a theorem?
That depends on the nature of the proof, what we
I
are
do
doing.
understand. I'm asking if you have an example, if you have come across such an example, where I can illustrate to the students the power of GeoGebra by not only illustrating something, but by proving something.
Yeah, we can use it in our lab activities itself. I have shared the link of that lab manual. Some examples are given in the manual, proving something or deriving something. For example, an activity is given to derive the equation of a plane. If some conditions are given. So some examples are there in the.
Okay, you recommend going to the lab, right? Lab manual.
Yeah. I have already shared the link of lab manual. It is available in CRT Kerala site, and I have shared another link. It's a link to my Google Drive. From there, you can download all the applets, supporting applets of first year lab work.
Thank you very much, sir. Thank you very much.
And somebody asked the question in the chat box, how we can create such applets. A better way of understanding is that you can download it from that link, and you can go to the construction protocol of that applet. Then from there, you get an idea of creating such applets.
I just want to make two comments on the last two questions. The first one was, can GeoGebra be used or any software be used to prove a theorem in mathematics? I think, let me disappoint you by saying that no software can prove a mathematics theorem. But it can give a very strong hint, very strong insight into problems in mathematics, and then you can try to give a mathematical proof of it. Because all the softwares are built on algorithms which are already known proofs. So unless a proof is known, something will not prove it again. Okay. So I have said everything GeoGebra or anything else, any other software, Mathematica, Maple, or anybody, any software gives, it will not give you an exact solution, right? Unless you think it is a computer algebra system where you can get solutions, that kind of a thing, but very simple ones. So don't replace mathematical proof by a software. That is one suggestion. Don't give students a idea that that is possible. And secondly, where are the sources for making these applets? We had conducted pre-conference workshops, 9 of them, where we made an effort that teachers learn how to create applets. So I hope you have attended one of them. If not, as Ramanujam said, that when you have an applet, you download it and look at what is called the construction protocol. That will tell you the sequence of constructions that has been done to create that applet. But once again, the pleasure of the pudding lies in eating it, not seeing it. So if you want to understand, you should start making your own applets, be it for primary, be it for middle, be it for secondary. Any other suggestions, comments, questions? Makaran or Soumya, do you see anything else in the chat box?
No,
No, not really. Yeah.
And let me say that somebody said, is it available? Such kind of booklets, are they available? Madam, let me say that applets are available for all the topics of mathematics, be it primary, middle, secondary, UG level, and everything. So I think you should make a group of your own where you try to collect and try to map it onto something that your curriculum is of that particular state. But Kerala has done it for their state level. I'm sure, for example, in Maharashtra, there is a group I know of, which has been part of my workshop kind of things, led by Shamsuddin and Kulkarni and so on, who have done it in Marathi. They have prepared a booklet in Marathi to help teachers in Maharashtra to learn GeoGebra. So at least the first step would be to make a booklet in your own regional language for those kind of things, to learn GeoGebra, and then slowly take it up. This effort of Kerala group is not a one-day effort. It has taken, as Ramanujan said, they began in 2007 after attending the Time Conference. And that was the spark the Time Conference gave them to start working on these things. And 2007 and now it is 221. You see how long the journey has been, how much effort they have put in to get to this level of achievement. So paths are not easy. It takes time, efforts, and passion. I know that there are passionate teachers like Ramanujan and Kerala who are keen to build a strong foundation for teachers to learn, for strong foundation for students to learn, and help them in every way they can. Any other? I'm just, whenever I get an opportunity, I go gaga over Kerala group, because I came in contact with them in 2009, and when they were beginning to do it, and I knew that it's going to be a great effort helping teachers. Yeah. So anybody else would like to say something? So if not, please get in touch with the Ramanujan and group if you need any help in creating something similar for your school, for your state, for your group of schools. And I'm sure they'll be more than willing to help you in creating such resources.
Professor Rana sir, just one comment.
Please. Yeah, please.
Yeah, you already said, I mean, I just want to kind of add, you said that teachers can form a group and then create such applets, etc. But I mean, starting thing could also be like you look at your curriculum, and if you look at GeoGebra, tons of applets are available. So maybe you can just collect for the time being and map it to your curriculum and just share, keep it at one place. Even the link itself, that itself will help, and then teachers may get motivated.
Yeah, sure, Ajit Kumar. I think that is a nice idea. And that is what is the beginning of a effort. That is what Kerala group had done it. They had first mapped on the activities, applets to the textbook, help book, they were called, and from the help book evolved this manual. So that is a stepwise process. I agree with you. The same effort has been started with the Marathi Shamsuddin Attar group has in Maharashtra. They have started doing that, mapping to the Maharashtra board curriculum. They have started. So these efforts is the teachers, because they are the users, they are the conveyor of knowledge to students. So if they do it, if they make an effort and they promote it in their school and among students and teachers, that is the best thing. Slowly the curriculum developers will realize, yes, we have to make an effort now to at least support them to do such kind of things. So you have to show your passion. So I think if no more questions, let me thank Ramanujan and the group for their tremendous effort. Keep it on. And as and when you develop an activity, another booklet, I know that secondary level +2 level is going to be on the slated. As yes, you already released.
No, it is in the final stage.
Final stage. You told me that. So as and when please do let me know so that I can popularize it.
Yes, yes, sir, definitely I will share it.
And I'm happy that at least in the starting one is in English. Whether you translate it in Malayalam or not, that is not that will be also a good effort. But English is mostly known and sort of comprehensible by most of the teachers in India. So thank you very much once again. Keep up the good work. And so we'll stop the session here. And
sir?
Yes.
So before going for
Yeah.
the break, can we have a poll, a feedback poll from the participants?
Yeah, please release the feedback poll so that we for the sessions today.
Yeah, it is launched.
Yeah, it is already launched. Please fill the feedback form so that we have an idea that when we organize anything next time, what kind of more things we should include in this. So the next session will be at 2 o'clock. We have a 1 o'clock, I think. Today we're meeting at 1 o'clock again, Makran.
Yeah. From 1, we have next
Yeah,
talk.
1 o'clock.
1 o'clock we have the next session.
Thomas, yeah.
By another speaker from abroad. So please do join for that. Quickly have a bite because after that again continuously we'll be having lectures. So anyway, advantage of online is you can always keep a sandwich on the side and keep eating and while listening. So there is no problem about going for a lunch break or such things. But it's good to have a break in between. So thank you, Ramanujan, and we'll close the session.
Thank you, sir.
Yeah.
Thank you. Thank you.
So have you released that?
Yeah, can you see the poll on the screen?
I don't see on my screen. Probably.
Yeah, the participants can see. Yeah. We close in around 30 seconds.
Yeah, okay, I'll close it in 30 seconds or 1 minute, no problem.
Yeah, so 80 people have already voted.
Yeah. So number is 130 present in the audience. So I think YouTube is already released and in the YouTube, they are not able to see the feedback form. I don't know. Anything?
Yeah, for the YouTube, we have to make it separately because this is a Zoom thing.
Okay, fine. Yeah. No, because some comment came.
Yeah,
and
on YouTube, we have posted the attendance form.
Okay,
attendance
fine.
form 3.
Okay. Because people commented that they can't see that they heard the comment that poll, but they didn't see the form.
Sure. It's actually inbuilt in Zoom. We can't.
Okay. Probably for YouTube, we can release combined thing afterwards.
Yeah, we can do that.
Okay, fine.
Yeah, let's close.
For the just announce it for the YouTube listeners. A feedback form will be released later on for all the sessions of the day. Thank you.
Yeah, so now the results can be visible. Can you see the results?
No, I don't see. I only see.
Okay, so let me say, so around 80% people are saying great. They're enjoying, and 19% have said good.
Good.
Yeah.
So let me say not bad.
Yeah, most of them have enjoyed.
Yes. Okay, good. So let us end the session.
Yeah, okay. So are we going to end the session or keep the Zoom meeting on because we have the same link?
Yeah, I think we'll keep the meeting on.
Yeah.
And, I will say that we'll be back whatever time it is.
1 o'clock.
Yeah. Yeah. I'll share my screen and say we'll be back at 1 o'clock.
Yeah, sure.
Hello, Mister.
Yeah, someone wants to speak. Jumianto?
Yes.
Yeah, hi.
I am Jumianto from Indonesia. I am a mathematics teacher at Piyongan High School.
Okay.
And I will use your presentation to learn.
Hello.
We can't hear you. Can you? Yuminanto, are you here?
Soumya.
Yes, sir.
Shall we stop the YouTube streaming?
Okay.
That I don't know. I mean, if we stop it now, whether it will. I think it's okay. We can keep it on. It's not a.
Okay.
Yeah.
Yeah.
Maybe we want to stop the recording since nothing is happening now.
I don't know whether we can start
I
recording.
will pause it. Yeah, I have already paused.
Yeah.
Okay, fine. Yeah. Somebody was trying to talk. What happened?
Yes, I am Jumianto from Indonesia.
Yes.
I need to your presentation to use in my material with my student. So I promise to use it. Okay.
Yes. What do you want to do?
I will use your material in presentation to learn my student about GeoGebra.
Good, good. That's very good. Thank you.
Okay, thank you, sir.
Thank you.
Sir, can you make the font a little bigger?
I'm trying to format it, but I don't know how to do it.
Okay.
How do I format? Whether I have to select first and then format, or?
Yeah, maybe.
I think you need to select it. Like
Yeah.
text.
Yeah, that's what I thought. The natural thing should be.
Right.
Yeah. I think it's too big, I think, probably.
It's okay. It's okay. Yeah.
Yeah. We'll be back at 1 p.m. That is good enough, I think. Visible, can move it to the center, probably. Yeah. Okay. So let me Soumya. Professor Thomas. Hello. Hello.
Hello, this is Thomas.
Hi.
Hi.
This is Rana.
Sorry,
This is Inder Rana.
I am not on video yet, no. But I think we still have about 20 minutes or something, right?
Right. We have 20 minutes. I just wanted to check whether you want to.
Okay, now I see you at all. Are you, who are you?
I am the one who sent you the invitation.
Okay, hi.
Yes.
You don't see me, but I said hi anyway.
No problem. Yeah. Yeah.
Okay, everything is working fine, and I guess I will be on 8:30, right? Or well, in 20 minutes.
Yes, in 20 minutes. That's right.
Yes, right. Okay, I'm ready.
Right. You want to test whether your screen sharing is okay?
Yes.
So
I hear you and I see you. Hopefully I will be seen and heard too, so I'm fine.
Okay.
Okay. Are you having lunch?
Just finished it.
Yeah, I just finished my breakfast.
Yeah, I thought so.
Yeah.
I think you are around 11 hours behind us.
4.5 hours behind you. Yeah, that's right.
Yeah, fine. Okay.
Okay, and I have contact with someone called Makaran, who is a PhD student, I think.
Yeah, he is here.
I am a postdoc.
Here's Makaran too. He's
Yeah,
coming
hi.
up here. Hi, Makaran.
Hi.
Oh, you
Are
don't
you able
see
to turn
me,
on your
but
video? Yeah.
Do you know? Remember meeting somebody by name Janaki Ghosh?
yeah, I know her well. Yeah, we've been collaborating for many years.
Yeah, so she'll also be joining.
She's from New Delhi, I think.
That's right.
Or in New Delhi, or whatever you say. Yeah.
Yes, sure.
Yes. We have been writing a lot together. I met her many years ago when I was in India. In Bombay, actually. I was in Bombay.
Great. So normally what the tradition we have is we'll request the speaker to say a few words about himself.
Yes, okay.
And then you can continue your presentation.
Great.
Yeah.
That will be fine.
Yeah. How is your book Modeling with GeoGebra doing?
The Swedish book is finished and about to be published, and the other one is on the move, so to speak.
Oh, good. Yeah.
That will be in English, so I'll send you a link when it's finished in the autumn, I guess.
Yeah, please. That will be nice.
Hmm. Has everything worked fine? The conference started this morning, right?
No, yesterday morning we had one day already under our.
Okay.
Yeah.
Oh, great.
And we have one more day to go.
Right. And do you have any physically people on board, or are all on internet? It's all digital, I guess. Yeah.
It's a purely virtual conference.
Yes.
So Janaki has joined. Would you like to say hello to Janaki?
Okay.
Janaki. Hello, Janaki.
Hello, good afternoon, sir.
Thomas is here.
Yes, yes. Just a minute. It says the host has stopped my video, so.
Okay, I'll ask. Makaran, can you enable video for Janaki?
I think you have to do that. As in, I don't have the permission.
As a co-host, okay, I will do that.
Let me just try.
I will do that.
So I think I can now. Okay, yeah. I just did that.
Okay, you did that. Okay, fine.
Yeah, hello, Thomas.
Hello, Janaki.
Hi, how are you?
Hi, I'm fine. Good to see you.
Yeah, likewise.
Mm.
Okay, so I will be starting in another 15 minutes, right?
Yes, we have around 15 minutes more to go.
Right.
Yeah.
Is there a sound coming from my background? Anything which is?
I don't know, because there are a lot of people on board anyway. So who is making what sound, we don't know.
No, actually there is a construction going on. I mean, I've told them not to do any sound, but you know how it is. So anyway, I'm using my headphone, and after introducing Thomas and while he's speaking, I'll keep myself mute.
Yeah, that will be
And
fine.
at the end, I will, and if there, of course, something that needs to be done.
Yeah, fine. No problem.
So the sessions went well in the morning. Actually, I had so many classes that I could not get away from them because I wanted to be free for the rest of the afternoon. So
right. No, they went very well. Chris lectured about 3D and modeling something in 3D. And it was nice, slow, and more like the workshop mode, so everybody sort of could do it along, kind of a thing.
Right.
And this Ramanujan was more recorded video, but about the manual they have prepared, GeoGebra manual, to the curriculum of there's a great work, and everybody wants to the copy of that kind of thing.
Right. Yes.
That was nice. So both sessions went out well. I think till now we have been having a nice, smooth sailing, and hopefully it will be same for the coming.
So how have you been, Thomas? We've been on touch on mail, but
I'm good. I'm retired from the University of Gothenburg, but I'm working more than ever, so I'm fine.
I think Professor Rana will be able to relate to that. I think you've been busy, equally busy, if not more.
Yeah.
So I think to formally retired from your duties, you tend to spend more time on what you like to do.
Yeah.
And you do it more.
In a way, yeah.
Yes,
Mm.
that's right.
Yeah.
That's right. So how's weather in Delhi, Janaki?
Yeah, it rained a bit last evening, so it's very pleasant today, but it has been
Great,
getting
great.
warmer. Yeah.
Great, but maybe a bit more humid now. That means.
Yeah, it's quite pleasant and not yet humid, but if it persists, it might become.
Okay. But,
You don't have any snow, do you?
no,
No.
not
Not in
in the
Delhi.
plains.
We
We have,
got a lot of snow in Gothenburg yesterday. So,
yeah.
oh,
Yeah, I think like the north part of everything is snows.
yeah. Yeah.
North of India, up in Himalayas, Kashmir, Ladakh,
Yeah. Okay.
we
Yeah.
have snow there, right? Mm.
So people have been leaving the session, I mean, going away and coming back, or mostly people are logged in, I guess.
We have kept it open that they need not log out.
Right.
Because that saves us the trouble of admitting again.
Yes, that's true.
And if you want to log out and log in again, you do it. Then we will admit you anyway.
Yes.
So that's
No, I'm okay. I just.
no. We increased the seating capacity to 500.
Oh, okay, wonderful.
So thinking that already registrations were crossing 200.
Right.
But more people will join probably. For example, at present, 55 are already on board.
Yes, I can see that. Yes.
And they are listening to us.
Yes. Keep chatting.
Yes. Right. Thomas, in your schools in your neighborhoods, how is the penetration of GeoGebra or such tools in the school level?
I think it's more than we know of, actually. As far as I've seen, a lot of schools are actually using GeoGebra, but not extensively. It's in small sessions and it's part of the exams and so on. So, but I think it's coming more than it's so to speak public in a way. Yeah. I have no figures though, so.
No, I'm just.
Yeah.
Yes, like earlier when calculators came on the scene, I think schools picked up calculators quite fast in the US.
Yeah.
So, do you think the intensity is something comparable to calculators and GeoGebra softwares, kind of thing?
Yeah, maybe, but the calculators could not communicate between them. So I think that's the difference for teachers, that they have to sort of use exam mode and that kind of stuff in order to get it accepted in the exam. I think that's the main issue in Sweden in a way.
Yeah, I think evaluations and assessments using technology is always a problem.
Yeah. And teachers never trust the students.
If something is written down and the answer is unique, then fine. Then we know how to evaluate.
Yeah.
But I think Sweden anyway has a lot of technology orientation in the schools in one form or the other.
Sorry, I didn't hear the first part.
I'm saying in Sweden, for example, there is a more of technological penetration rather than compared to other European countries.
I don't understand what you're saying, actually.
No. Okay.
Please rephrase it.
Yeah. See, what I'm saying is, as far as education and technology is concerned,
yeah,
how would you compare Sweden versus, say, UK or France or Netherlands?
Sweden and Norway and Denmark have about the same school system with compulsory school for 9 years or for 10 years now. You start when you're age 6 and then you go to when you're 15. And then you go to upper secondary school or gymnasium as we call it. And then you go to the university and you have to select the right program at the upper secondary school in order to be accepted to university programs and so on. So we still have the same systems as we had when I was young and when my parents were young and so on.
Okay.
What's changing is the programs at the upper secondary school that you can take, of course.
Okay. I think Germany has a similar system probably.
Well, my understanding of Germany is that Germany have 16 different systems because of the 16 different states that never agree about anything. But some of them are very old-fashioned, actually.
Okay.
I think so. Germany is a strange country in many senses, or states. Yeah. I hope no one from Germany hear me.
No, it's okay.
In case of they have to correct me in case of that.
Yeah, but what is effect is effect.
Yeah.
In a small country having so many different.
Yes, there are only 10 million Swedes, so it's easier to agree.
Yeah, yes, that's what I thought.
Definitely.
I think it's not strange if in India you say that there are 10 different state systems of education or 20 different states, but in a small country like Netherlands or Germany or France or any European country, it should be not difficult to agree on.
France and Germany are big countries.
So from European standard.
Yeah, from a European standard, they are large in that sense. But Sweden is a small country and a rich country too. So
yeah, that's
in a way, it's special in that sense.
That's right.
Yeah.
Well.
Sir?
Yeah, Somya.
Yeah, can you please make Dr. Janaki a co-host?
Yeah, sure, I will do that. Yeah.
Thank you.
Yeah. Right. So Janaki, when you feel it's 1 o'clock, you can.
Yes, I'll start.
So I have already requested Thomas that will announce your name and affiliation, and he can say something more about himself also. If
I have an introduction. I can use it if you like, or you would.
Yes, I'm happy.
It's up to you.
Yeah, whichever way.
Okay. I will introduce him if that's all right.
Yeah, fine.
So sure. You can just say his name and then I'll introduce.
No. I'm not saying anything.
Okay,
you are in charge of everything.
Sure. Okay.
Yeah. You can introduce yourself if you want. That you are chairing the session.
Yeah, I'll do that. In fact, I'm meeting Thomas after 11 years, Thomas? I'm seeing you after 11 years. So we've been over the years.
We have been collaborating a lot.
Yes.
It's good to see you.
Yeah, likewise.
Mm-hmm.
I visited Gothenburg in 2010, Professor Rana.
Yeah, I think
there was an Indo-Swedish study actually.
Yeah, I think.
Meeting, so, and then Thomas had come down to Homi Bhabha Center, and that's how the collaboration started.
Oh, great.
Yeah, yeah.
So another 3 minutes.
Yeah.
3 minutes more, right?
Thomas, would you like to see screen share working okay for you?
I think it's gonna work. I use this a lot, so but I can share my presentation.
Yeah, you opening short, you can present, and then
Yeah,
we'll take over.
yeah. I don't think this is in.
Yeah, it's okay.
Yeah.
Do you see that?
Yes.
Great.
Perfect. Okay, so 1 minute to go. And,
This is an amazing way, actually, isn't it? Is this the future that we will all be doing this, never travel anymore?
yes, seems like it.
Yeah, yes.
It's quite possible, I think. At least I have gotten used to this system, new one, not traveling at all.
Oh.
Yes, I do miss the travel though.
Yeah, that is
Yeah.
travel for pleasure is something different than travel for necessity.
Yes, that's also true. But academic tourism, as they say, is
Yeah.
so it's 1, so should I start?
Yeah.
Okay. So a very warm welcome to all the participants to the next session of this GeoGebra conference. It is my great pleasure to introduce the speaker for this session, Professor Thomas Lingerfrod, who is retired from as a professor of mathematics education from the University of Gothenburg in Sweden. And needless to say that although he is retired, he's still teaching mathematics and physics at upper secondary school in Gothenburg. He has written many books, and in fact, he's just finished a book about programming, which includes GeoGebra, Python, and Wolfram Alpha in mathematics. And he's working on yet another book on the same tools for mathematics and physics. Thomas did his PhD in mathematics education from the University of Georgia in the USA in 2000, and he has served numerous positions as professor at the Galway University, Sweden from 2010 to 12, and his previous academic positions have included being associate professor at the University of Gothenburg in the Department of Education. He has taught myriad courses like probability and statistics, calculus for teachers through dynamic geometry software, elements of modern mathematics, mathematics education, algorithmic number theory. So there's a vast a number of courses, variety of courses that he has taught, and he's also involved in very important projects. So in 2008 to 10, he was a part of a European project on developing quality in mathematics education and mathematics education for digital generation, encouraging ICT usage in the classroom through a school and university partnership. Since 2018, he is working on a programming project with the aim to teaching mathematics and physics. So I think that maybe he'll be showing us a glimpse of that in this talk. So it's my great pleasure, Thomas. Welcome to this conference, and we really look forward to your session. So over to you, Thomas.
Thank you. And my thanks go to the organizers for inviting me, and I hope we will have a good time. And thank you for the presentation, Janaki. Far too good. Okay, in every conference session, there's also a problem about how to get the stuff that you're watching. So I just print my email address here, and if you want to send me an email afterwards to get my slides, I will be happy to do so. So now you don't need to print or copy or record or whatever you're doing. So I will try to give you snapshots of what we can do with GeoGebra. That's all we can do in 40 minutes or what we have. So assume we like to summarize all 5-digit numbers divisible with 7. This is almost impossible to do by hand, I guess, but easy to do with GeoGebra. What we have to do first is, of course, to find some numbers that are 5-digit numbers and divisible with 7. So I give you just a hint of how to do that. You can watch that later on. We find that the first 5-digit number divisible with 7 is 10,003, and the last one is 99,995. So that's what we need to have for GeoGebra, or the factors of that numbers we need to have for GeoGebra. And why I'm showing you this special programming sentence is that it includes sequence, which is a very important command in GeoGebra programming. You can do that you can use that in many different sentences, in many different ways, the sequence. And you see that we have a relation. We need to have every 7th number of k, and k is the variable, and we go from 1429 because 1429 times 7 is just that 10,003, and we go up to 14,285. And this list creates all those numbers directly, I would say, on any computer or even on a smartphone. And then you just sum it. So you have 2 lines. One is the list, and then you have the sum command, and you get the sum. And this is from my book, so I know that Python and Wolfram Alpha actually also do it similarly and get the correct sum. So the sum is correct, so to speak. And this is an interesting part of GeoGebra that perhaps not all know about, that you can do a lot of number theory problems in this way, as long as you keep it within the range of precision of 15 digits. That's one part. Another number theory part of GeoGebra is that you can select prime factors from numbers, and you can actually go up to 1 million, which is impressive, I think. So you can attach this to a slider, so you have a cooperation between the GeoGebra graphic window and the cast window, so to speak. And then you can just use the slider and draw that. I don't show you the GeoGebra files now because we are in a hurry. Maybe I will do that later on if I have time. But right now I'm just keeping the time, so to speak. And you see that we get the prime numbers of 183, or the prime divisions, or whatever you call it, and that's 3 and 61. So this is also an interesting part of the GeoGebra behind the scenes, so to speak. Of course, you have all these programming possibilities with 3D now in GeoGebra, and you can do that in order to illustrate or visualize, in this case, a cylinder and height and radius and so on, and to connect that to, in the graphics window, to cylinders. So you see here a collaboration between the graphics window 1 and 2. I have people are entering the room. I see that all the time, so I don't know why. It's sort of in my screen. I don't know why. And you can also use that graphical or geometrical representation of the ratio for instance, showing decimal or percentage formulas as part of the whole and the whole. And you can connect that also to sliders. So I think that that's in a learning sense, the possibilities to vary or use variation is very important, and that is connected directly to the sliders, so to speak. You can use GeoGebra to show numbers in different bases, which is part of the Swedish curriculum as far as I know, and which is also, I guess, part of many different curriculums around the globe to show numbers in different bases. And here are base 2, 3, and base 16, but you can of course program GeoGebra to show any base that you like to translate numbers into. Talking about that sequence command, you can use that sequence command to divide circles into equal sectors, and then you can represent rational numbers in that way. And here is one perhaps overloaded construction I've done, but it shows the possibilities of GeoGebra, and you can also have this connected to the numbers below. So when you move the sliders, the numbers are recalculated, so to speak. So all objects in GeoGebra can in a way be programmed in that sense that you can sort of relate them to each other, and you can use variables to relate them and to also change all that. And I will just show you one way to do this. You don't have that now, but if you want to, I can send that as long as well. It's about learning students how to find values for a point on the x-axis in this sense. And actually you can sort of expand this exactly the same programming sentence in order to make students find a complex number in the complex plane. It's just to add one dimension, so to speak. So this is an interesting part of GeoGebra, that you can sort of program a lot that has to do with position and to a communication and new position as a point there. So what you do is that you have to define a point, of course, and if it should be on the x-axis, then it's that I is equal to 0, and then you construct it with a random number. You can use random numbers in different ways in GeoGebra actually. And then you need an input field, and you need a control if the guess is correct or not, and then you need some sort of collaboration saying to the student not correct, try again, or something, or correct. And you can find a GeoGebra file over there. In Sweden we use Celsius. In US they use Fahrenheit, and there is always a couple of examples in exams in Sweden how to translate between them. So you can also program that in GeoGebra, of course. And here is a graphical display that's showing this proportionality going through a 0 number in that sense. In upper secondary school in Sweden, we are talking about kvadratkomplettering in Swedish, which is completing the square. I don't know if you use that method, but in Sweden that is kind of still important in order to understand methods for solving degrees of second degree, or equations of second degree, sorry. And this is one such construction in order to, and this is related to Al-Khwarizmi, so you can sort of make it a cultural historical angle as well. and show them that this was known, well, many years ago. I'm not quite sure, but about 800 or something in Spain. You can do arithmetic with the complex numbers in algebra. You can sort of use the 4 arithmetic methods with addition, subtraction, division, multiplication, and then you can sort of change the 2 original numbers and you can see what happens. And this is one such example. Easy to accomplish, easy to do. And GeoGebra understands that if you write a number 2 plus 2i, then it's a complex number and it will be labeled Z1 and so on. So it's really interesting, I think, at least. I'm just checking my time here on my telephone. And if you want to, you can also create random functions, and I've chosen a random trigonometric function because it's interesting in the sense that you can't really have 0 in that, so you have to and now you don't see all that I have here. Can I take away that? Yeah, I can. So if you want to you see that we have 4 variables. We have amplitude, and then we have k and x and w. So plus c. So we have to not x, of course, but we have 4 variables, and we have to sort of randomize them in some sense. And if you do that, you can't have 0 for a and k. And then you have to construct them as a random element instead, which is very neat that you have that in GeoGebra. You can both have random between and random element in. Then you can omit 0 in that. If you do this, you understand what I'm talking about here. And of course, you can have some sort of construction when you have a button that you press for new trigonometric functions and so on, and GeoGebra will do that instantly. You can handle implicit functions. I have a lot of information up here, so I don't say, but I know that I have written implicit functions here. So that is not so easy for. And this is the leaf of Descartes in GeoGebra, x cubed minus 3xi plus u cubed equals 0, which is interesting sometimes if you want to, if you look into what's been done there. And of course, you can use GeoGebra to teach calculus. This is just one integral between command. In GeoGebra, if you want to calculate integrals, you start writing integral, and then you get options as you get with all other programming commands. And this is just one of many things you can do with integrals. Okay, I'm speeding on here, but that's because I want to come to the physics. And I'm gonna see if this works. Perhaps not. Perhaps I have to. I'm not sure that you will see this. So maybe I have to leave my sharing. I'm stopping my sharing now, and I will share something else. The problem with Zoom is that you can only share one. I have to leave this. I'm not sure that I can do this. Okay, do you see this now?
Yes, we can see.
Oh, great, great. Okay, so let's start. I'm not sure where I am. Here we go. I guess I've tried to find things that are general in most curriculums. This is a pendulum and a sine graph that it creates if we look at the amplitude over time, which is illustrated by GeoGebra and should stop over there somewhere. And then you can also do a regression and find a sine curve that fits with that more or less, or at least, or pretty good in the beginning and not so much in later on. And this is part of what I'm doing in physics, to try to illustrate isomorphism between mathematics and physics in that sense. It means something, but it's still the mathematical tools, so to speak. Okay, that worked well. So I stop sharing. And then we take back the, yeah, here we are. So that's one thing in physics that you can actually create with GeoGebra. And I have created, but I haven't translated them to English yet. It's downhill skiing, which is interesting because you can sort of look at the translation of potential energy into kinetic energy when you're going down. And then you can talk about friction, because not all of the potential energy is translated into kinetic energy, because you have to sort of use your skis to slow down or stop and so on. And then you have the position of velocity switch, which is also interesting because it's already in a compulsory school in Sweden. And you can have different ways of showing the translation between a position and the velocity of an object that is moving. And that is normally very difficult for many students in Sweden, at least, to understand. And I have also programmed a box sliding down a plane in order to talk about friction and about the sliding plane's elevation, so to speak, how far up it is or not. If it's like that, it also obviously is a free fall. So maybe I don't show them. I'm going to show you something else instead. Yes, I have written many articles about mathematics and GeoGebra, and here are some of them. And you see that the share this is part of this publication as well. But I also written 2 articles about physics. One in the Electronic Journal of Mathematics and Technology in the US. It's about modeling between mathematics and physics, and one is about dynamic athletics for teaching physics, which is accepted for publication but not yet accepted. And I'm going to try to show you, but obviously I have to. You don't see this, I guess. Do you see this? No, you still see it. So I have to stop. New share. Okay. And I can show you, perhaps I can show you that this directly. I'm pretty impressed by this myself, so I'm sharing it. Do you see electrical circuit now?
Yes. Yes. we
Yeah,
can.
great. Yeah, great. So I'm gonna take off the switches. This is an interesting way to illustrate. Of course, students have to accept that the bulbs are the round, the circles and with an X in and so on. But you can nevertheless sort of illustrate what happens. You have to switch 2 or 3 in order to get them to shine, of course. And if you do this, they shine equally, okay? But if you do this, you see that this one shines more. And I've tried to illustrate that with a little brighter light and with some, because it gets all the current, and you can check the current. You see that there are 22 amperes, so that it will be 22 amperes going through that as well, but not so much about through these, which is very interesting that you can sort of program this to be shown in an applet, I think at least. So I'm gonna take a new share. Do you see this article now? Dynamic applets for teaching physics.
Yes.
Yeah, great. Basically one of the applets you just saw. And it's here. And the other applet is about resistances in circuits. And I think we can, and I can use share, which is that, I think. You see this elaborate the construction now?
Yes.
Yeah, great. And let's see, perhaps I need to, yeah, you see it over. So let's see what happens if I sort of change the resistances. Of course, I'm talking about physics now, so I hope that you all have some sort of relation to physics. This is an interesting part. I think you see that all the calculations are changed or recalculated, and all the also in the image we see what happens over there. So you get the idea that the possibility to illustrate something and to share this, especially if you are teaching over distance, are of course enormous in that sense, that you can sort of share this with students on their own computers, just giving them a link, and then you can sort of help them to elaborate and to answer questions related to the construction, so to speak. And this is not so complicated to do, as far as I know, at least. Yes, I'm gonna try to get back to my share. Or you can actually select multiple windows. I didn't know that. I haven't done that before. Perhaps Zoom is changing as well. Oh. Do you see the PowerPoint
Yes.
now? Yeah,
Yes.
great. So maybe we should look at the downhill skiing as well, although that is okay. Are you seeing a skier?
Yes.
Some Swedish text. Okay, so it says that the skier's time and the skier's I have to take away that height is 600 meters, and it says in Sweden when the skier starts his path downward, potential energy is translated to kinetic energy. And when the skier is losing height and potential energy, the skier's velocity increase, and thereby also the kinetic energy or velocity. That is a translation of skiing. And what is interesting here is, I think at least, is the programming sentence. This is a curve that I have selected in order to make it look like a ski hill. I am very fond of skiing. Actually, I will go in a week to the north of Sweden and be skiing downhill, perhaps in a slope like this. And then there is a point on object moving here, and there is an image of proper size that I have attached to that point. So it goes like this, if I can start this. And you see that the potential energy, I haven't added any friction yet, but that is of course something you can do and perhaps attach to a slider. And then it will be in English, I promise you. But this is a way to show you how I think about programming in this sense, okay? So I go back to my stop sharing and new share. I guess we don't have time for questions, right? This is not a talk in that sense. No questions. Right. So I have.
You have about 8 minutes more for your own presentation.
Yes.
And then you can ask audience if there are a few questions.
Okay.
You have 40 talks, another 8 minutes or so.
Right. I will show you some more of these. Do you see this air resistance slide now? Yeah, great. Something rather complicated in physics is to understand air resistance. Of course, students are learning friction early in their lives. They're learning friction when they are skiing or when they are ice skating or when they are sliding in a slide, for instance, and have different clothing on and so on. But air resistance is difficult to understand, especially if you compare it to free fall. So I've been trying to work on a construction of that, especially if you drop something from a plane, which is a weird situation, of course, but we are getting there. So you see a plane, which is possible to, and you see something that is dropped from a plane, and you see that it has a velocity in x direction that is not changing. It is under the plane if we have no air resistance, but it has some sort of free fall acceleration down depending on gravity, of course. So gravity sort of directs you down. And the interesting part here is that this is a parabola, second degree curve, of course, because the gravity has V2 or power 2 constant, or variable. So, but the part here is, how do you understand air resistance? Air resistance will affect the package that was dropped, and you have to have a possibility to view the air resistance curve as well. Okay. So this is what we can do. And you see that the air resistance is hindering the curve in some way if you view it over time. Okay. So it's possible to, and where is, here it is. You don't see this. No, you don't, because I don't have that share screen. In general, I think that I can. And we can also show, look at the box sliding, which has also importance in understanding the third law of Newton, actually, that if you sort of hit something, it hits you back as well. So we are going to look at that too. No, we are not. We're going to look at something else. Are you seeing a class?
Yes.
No. Yes. And you see we can change the elevation or the slide direction or whatever you call it, and then we can change the friction. So this is about friction actually, but there are also forces in this box that is sliding down. All the text is, of course, in Swedish right now, but you can understand the concepts of this, okay? I think I'm about to...
Yes, it is time for the, we can maybe conclude and we can have questions from the audience.
Yes.
Would you like to conclude your talk?
Yes, I like to say that to program in, my book is about programming in GeoGebra, Python, and Wolfram Alpha. And GeoGebra is sort of proving that is, in order to construct situations in physics, it's impossible to find any other tool that is as broad and acceptable as GeoGebra. I think it's amazing what you can do actually in order to illustrate conceptual understanding of situation as we often do in physics.
Right.
I guess that's my conclusion.
Okay. Thank you, Thomas. There are a lot of appreciative comments and from the audience, and there are some questions which I would like to share, which have come already in the chat box. That can we use GeoGebra for sequences and series? There are certain topics people have mentioned. So one question is, can it be used for exploring sequences and series? I can ask the questions one by one if you would like to respond.
Yeah, okay. Okay, what was the question? Can I read it here too? Is it from the chat or
Yes,
what
it's
do you
from the
take?
chat. It says
Okay.
about whether GeoGebra can be used to explore sequences and series as a topic.
Yes. But I don't see that question that you just read to me.
Yeah, I have noted it down.
Okay.
And can numerical methods be used in GeoGebra to obtain solutions? So
yes, I would say so. I read something about Canada Plus and Fourier be used in GeoGebra to obtain their solutions. I think that is difficult, but I don't know. I haven't tried it. So Fourier analysis is about curves, so it should be possible. Yes, yes. But beware of the complicated mathematics. Perhaps that's, well, yeah, I would say that I would try, but I haven't tried.
And linear programming is another topic that we
all kinds of regression analysis is possible in GeoGebra. You can use the possibilities to model with the models that GeoGebra offer you, but you can also define your own models as m of x, for instance, and then you can sort of use that instead.
Right. And everyone wants to know whether they can access the beautiful applets that you have shown, and the articles that you shared. Whether they
are if they email me, I can show my email address again, perhaps.
That would be
yes. So if they email me, I can offer everything. I have much more than I showed here, of course. Do you see that email address?
Yes.
Yeah, okay. So it's just to email me and I will share whatever they want. The presentation, obviously, but also all the links and so on.
Wonderful. Any other questions? I think somebody Midhushmita wants to know whether we can use GeoGebra in fluid dynamics to obtain various graphs of temperature, velocity, radiation, and so on. So,
let me say it like this: you can use GeoGebra in everything that needs some sort of graphical interface. So if there's something to be graphed, it's possible, yes, with some limitations, of course. Yeah.
So if there are no more questions from the audience, I would like to.
Can I just
yes, please, sir. Please
say something?
Sure.
I think it may be interesting for the teachers and others to know that, of course, Thomas has not touched that issue at all because of limitation of time. The partial differential equations and solutions of partial differential equations can be solved using GeoGebra. There is a command called numerical solve, and I use that command to recently to make a pandemic solution for the growth of COVID-19 virus. So it's possible. I think, as Thomas has pointed out, the programming of GeoGebra can be used in while various varieties of ways in maths, physics, biology, botany. Of course, mathematics is more or less same as physics, and physics is almost same as mathematics as far as the problems are concerned. So I think almost every field in physics, after all, balancing chemical equations is same as electrical networks, is same as solving linear equations. All are same. So I think it's a new sort of thing that has opened up GeoGebra, and Thomas has brought that how it can be used in physics, various problems in physics. So thank you, Thomas, for that. And I think this is up to the teachers to explore and get into the things, and contact Thomas for more information. And go ahead. Thank you.
Thank you, sir.
Thank you.
And one last question, Thomas. I think somebody is asking Dr. Harsha that is there any book which includes basic to high level programming? Would you like to recommend some books to the audience?
I haven't seen. Yeah. In the fall, it will be in English, the book I'm writing, but I'm not sure. I haven't seen anything about GeoGebra programming yet. No. But there are a lot of books about programming in Python, of course, and in Wolfram Alpha, perhaps it's as well. Let me just say that if you want to do some heavy number crunching in any sense, then you should not use GeoGebra. GeoGebra only works with 15-digit precision, while Python and Wolfram Alpha can work with 250 digit precision. And that is a huge difference if you do something that requires a lot of mathematics in that sense. So I wouldn't use GeoGebra then, but I would use GeoGebra when there is a situation that needs to be translated into a coordinate system. Okay?
Okay.
Okay.
So, thank you so much, and I think it's been a wonderful session. You have shown a completely different side and glimpse of GeoGebra, Thomas, for usage in physics, and in fact, you've shown examples in application of GeoGebra in number theory, sequences and series, some calculus examples, and in physics, you have covered a wide range of topics from electrical circuits to air resistance and friction. So, with that wonderful collection of examples, I think it shows us how versatile the software can be if we use it appropriately, and that's true for any technology tool. We have to keep finding these creative ways of using the tool to our advantage, to the advantage of our students. So thank you so much for that wonderful presentation.
Thank you, Janaki.
Thomas, let me, as a convener, let me thank formally for you taking off time and making an effort to come to Indian audiences and exposing an aspect of GeoGebra in physics. Thank you very much. We'll be
Thank you. Thank you. Thank you for inviting me. Thank you.
welcome. Sure.
Thank you. Bye-bye.
Bye-bye.
Bye. Take care
Thank you.
and enjoy your skiing.
Oh, thank you. Thank you.
Okay. Thank you, Janaki, for taking care of the session.
Thank you, sir. Thanks for the opportunity.
Yeah.
I think there are, okay.
Yeah.
There will be more sessions now, right?
Yeah, there is a next one is at 2 o'clock by Dr. Surendra Reddy on modeling using GeoGebra. So we'll take a short break till 2 o'clock. We'll be back at 2 o'clock.
Okay, sir. Thank you. See you then. Yeah.
Yeah, sure.
Sir, if you are there, can I just ask one question?
Yeah, please go ahead.
Yeah. See, if one has to kind of toggle between the PowerPoint and GeoGebra, I think if we keep both open, we can minimize one and show the other. That should not cause a problem, I think, right?
No, I think you keep both the windows open.
Right.
And share only one window.
At a time, yes.
At a time. That is one possibility.
Yes, yes.
I don't have any problem because I use a PDF and there is a link for GeoGebra. It opens and then I close that. I come back to my PowerPoint anyway in PDF. But for Microsoft PowerPoints, I think it's better to keep both open.
Yes, yes, right.
And toggle between the two, whichever you want to open.
Right.
So for that, you need to share the entire screen.
Entire screen, right.
Yeah, share your. Yeah, I think you have to share the full screen and then toggle between maximize and minimize kind of thing. You'll have to do that.
Yeah, yeah. Okay.
Sure. Ajit,
Sure.
you're already there. Good. So we have 10 minutes more to go.
Yeah.
Yeah. So let me just write on the screen. So,
हाँ मैं गया था बाहर
Hi, Ajit.
Hi. Good
How are you?
afternoon.
Good afternoon.
So nice to see you.
Yeah. You have given me permission to share screen.
I have to check. I'm not the host, so I don't know, let me.
I think you can make me a host. Host can make a host.
I'll just check who is the host. I'm co-host, so host is. I think Professor Rana must be the host. Let me come.
But you have option when you right click on my name.
I'm not sure. Let me just check. No, I don't see.
Okay.
Yeah, Professor Rana would be doing that. So he is the host. So.
Okay.
Soumya?
Yeah, hi.
Yeah, hi. This is, you're using this 500 participants license, right?
Right. Yeah.
Yeah, so I think you can disable now admit option.
Yeah, because problem, many people are in waiting. They are saying that.
Yeah, right. Because otherwise, I mean, you as a co-host, you have to keep doing admitting.
And,
So what exactly? Okay, you mean make it automatic?
You can directly join, yeah, without waiting.
You can remove the option
waiting room
option.
But we don't have a passcode. At least one of the check could be there. So I opted for this waiting room.
Initially, because since there are so many registered participants, that's a good idea actually. But
is it possible to do it now while the meeting is running?
Yeah, you can.
One can do, but I don't know whether it will be effective in this.
Yeah, it is effective, sir. The moment we disable waiting room, people can join.
Yeah, Dr. Surendra, can you just tell me how to do it via the settings in Zoom or from here in the meeting? Zoom.
I think when you click on participants, then there will be option if there is a more something like that, where you can as a host or co-host, maybe for under the once you click on participants, right side the tab will come.
I see. Okay, let me check.
There will be somewhere setting. There you can enable or disable waiting room.
Anyway, so Soumya, you are the host now, so you can make co-host to Dr. Surendra.
Yeah.
So it's exactly at 2 as per my watch.
Yeah, it's 2.
Should we start?
Yes.
Yeah, we can start.
Okay, fine. So good afternoon to everybody, and I welcome you all to this second session of afternoon of second day of this wonderful conference. The next speaker is Dr. Surendra Reddy. He is a PhD in mathematics from University of Hyderabad and currently working as a faculty in Swami Ramanand Tirath Marathwada University, Nanded. Apart from his regular teaching and research, he is someone who is very active in training teachers and organizing workshops for teachers. And during this pandemic, he has trained thousands of teachers on helping them in using these online tools, which can help them in teaching mathematics and various other things. So he also has a course in Udemy, which is quite popular. So he is going to talk on modeling using GeoGebra 3D calculator and testing through augmented reality. So I invite Dr. Surendra to start his presentation.
Thank you, sir. Thank you, Professor Haji. And yeah, I would like to thank organizers, especially Professor I.K. Rana, who asked me to give some talk on GeoGebra, some of the aspect, and he told me to explain some 3D related. Okay, so I think I'm audible, right?
Yes, you are audible.
So first of all, I would like to tell all the participants that there is no presentation. Whatever I am going to show, it is live demo. So, and also I am not that much expert. I am also very new to this, but I have learned things after, especially for this conference. I have gone through it. I have learned things somewhat deeply. As I said, you all get a good opportunity to explore. This is the best time to explore GeoGebra. So take this as an opportunity and go through this demonstration. You will definitely get a motivation and an idea how you can explore. And a lot of resources are available on GeoGebra website as well as on YouTube. I'll just go through this and then we'll immediately start because I have only 40 minutes time. And I hope I will cover 1 or 2 models we'll generate, create. I have following each and every lecture from yesterday. So whatever questions users are asking, I have noted down some questions and what points they are expecting. I will try to show these things, and organizers can stop me anytime if I exceed time. Okay, so let me share this screen. Yeah, fine. So as I said before, just going to this, you will see it is amazing, especially this GeoGebra 3D calculator. Very, very useful for mathematics teachers, not only mathematics, any geometry related shapes, whoever want to explain in detail, then it is very, very useful. I'll just show these some of the things people are asking. Someone asked, can somebody construct, is it possible to design a home just like I'm showing here? And it is possible. You can see here the advantage of this having this. Advantage of having GeoGebra is whatever resources are available, you can have this algebra. That means you can have the how they have constructed. You can change accordingly. You can learn each and everything from left side. So whatever you see on this left hand side, this one you can usually it is called as algebra or the code syntax. You can call it. If you modify something here, it will reflect here. If you modify something here, it also reflects here. Okay. So it is just like one side, right side is geometry and the left side is algebra. Whoever don't like geometry, you can construct everything from algebra. Okay. The other one is you can also ask somebody, for example, you see that this is a fish type thing, how one can construct using this surface command called surface, and how you can rotate things. It is a beautiful thing. Whoever want to learn more things about GeoGebra, especially 3D modeling, he is the best person. In fact, Rana has suggested me. After that, I have started following this fellow. Who is a great professor, and he almost all concepts he has covered. Brzezinski Math is a YouTube channel. Just if you explore his videos, you will get a clear idea. Whatever I have learned, even though it is little, I have learned from most of the things from this person, professor. So I suggest whoever wants some resources, how to construct something, you just follow this person. You will get ample number of videos for your basic learning. Okay. Then, yes, this Zoom disturbs a lot. Here, the other one which I would like to show is, for example, you have some shape. If you have some image of that shape, using that image, you can plot the points, and using rotation and all surfacing, you can actually construct the image, actual image, whatever you have taken from that. Okay, just I can just go through here and this process. After that, you can see that yes. So similarly, whatever image it is here, that image is constructed, modeled using GeoGebra. Again, this is explained by Brzezinski. So many videos are there. Once if you want to learn, you have an interest, you can learn very easily. Everything you can see here, what are the functions defined, how it is projected from image to here. These things, some of the things you can go through it. Now, yeah, for example, what I am going to show in this 30 minutes, whatever left, is how we can construct simple, because we are many, I assume that even I, as a basic learner, it is good to have some basic models to design and test using augmented reality. So I'll show this, how one can create a mug. Then somebody asked how this from parabola, how we can construct or demonstrate paraboloid, that you can see it here. And also the other one, which it's not here, I will show it later, which personally I like when I was teaching complex analysis, explaining that stereographic projection, or you can call it as Riemann's sphere. It is very difficult to explain on blackboard or whiteboard. So, but using this GeoGebra, I will show you how you can explain concept very easily. And while constructing that, I will show you what are all the main features available in GeoGebra. Okay. With this small quick introduction, let me start from the beginning. What we have to do it to use GeoGebra 3D calculator. Okay. Okay. Fine. So if you see, as everybody mentioned, GeoGebra, better to have a separate account, because whatever you create, it will be all resources will be shared here. For example, I have created some resources and it is available here. Anyone can access those resources. If you don't sign in, then these things won't be possible. You can use it, but you may not able to save it. You can only save it on your computer. Okay, so it is very simple. You can just sign in with separate email ID. You can create it, or you can sign in with Gmail or whatever email IDs you have. Once you sign into it, then whatever resources you have created, it is available. Okay, and you can use it and you can share it with anyone with a link. They can clearly get all the details how it is constructed with algebra. Okay, fine. Now let's go to a 3D calculator. How we can go to 3D calculator? If you go to GeoGebra homepage, then as everybody know by this time, these are all some of the powerful apps. So you click on this 3D calculator, or you can also access from here 3D calculator. So anywhere if you click, it will open. So you can see that here sign in says if we sign in and then do things, then all those things will be saved as our resources. Okay, and we can easily access those things. Fine. Now the first thing, which 5 to 10 minutes, I will show you how we can construct any 3D model, simple one. Then how we can access that using using augmented reality. Okay. So for example, I don't know, this is the one which I am going to construct now, and I will test it whether it fits completely with that or not, at least approximately. Okay. So this is just like a small cone type thing. Right now it is available in my office. So I thought I will construct a model similar to this, and it is easy, as well as why I have selected morning lecture. You have seen how to construct using prism, any just like cuboids. Okay. Now I will have taken a topic in such a way that here you will see how you can get some surface by using rotation or spin. That is the one of the reason why I have selected this one. Okay, so first what we have to do is we will construct, our main aim to is to construct a mug. You can call it mug. How we will do that? For that, the basic idea is we will have a line just like height. we'll join a line between 2 points based on a circle below a top as well as bottom. Then we will rotate that line 360 degrees to form a surface, so that a straight line, when you rotate it, it makes like, you can see that it sends like we are constructing surface which forms as a mug. Okay, so for that, first what we can do is before constructing, I can show here a demo. Then it is very easy to construct. For example, you see this, but the moment I keep on rotating, it is forming like a this mug, right? So if I disable this for time being, then just a second. It's taking little time. Yeah. So initially what the idea is, we have constructed these 2 points. One is this A on this axis, x-axis, and another point B on this z-axis, just like height. Then we have joined these 2 points using polygon. That also I will show. After this, what we did here is we have constructed a point which is a rotation. Okay. Then from 0 to 360 degrees. After that, we have used a command called surface. So we can generate surfaces using this command. Okay. For that, we have taken this function, which is function is nothing but simply line segment here. So we are and taken this rotation through this help of S, and we are rotating around Z axis. Okay. So if you make it S is equal to 0 degrees, so there is no rotation. And then once we start moving 90 degrees, 100, 180, 360 degrees, then you can see that it completed, and you can see that this is exactly looking like a mug. Okay. If you want, you can rotate, and you can see. Okay. So how we'll do this, instead of showing this one, I'll explain here that we can do it very quickly, and it is not at all a difficult, right? So that you will also understand, right? So first thing, as I said, is that we will put it, I have noted down the radius, what is the radius of base circle, as well as the radius of the topmost circle which we are looking at, and that radius, which I can show you later, is the base radius is 2.5 centimeters. So if we want to put a point from origin, obviously we want to put a point here. So I will write that as A is equal to, because it is an x coordinate, so 2.5, then 0, 0. Okay. So the moment we write this one, and now you can see here point A is at 2.5, it is placed, okay, on x-axis. Then next one which we will do here is another point which we would like to put, and here, so 1 point I have taken here. Now the second point which we want to consider is the radius of the top circle. That circle here for this mug, it is 3.75, and the height of this mug, whatever I am talking about, is 13.5 centimeters. Just to see that it fits into our model. Okay. So what is our point? V is equal to, here we want to have x, which is 3.75 this time, 3.75. Then y is 0, and height we require is 13.5. Okay. So if we put this, then you get a point. Where is that point? Yeah. Here is the point. Yeah. Here is that B. Okay. Now what we'll do is we'll try to join these two using polygon. For that, if you click here, of course, you can write it as algebra also, joining those 2 points and so on. But there are already available tools are available. There are n number of tools are available. Point, pyramid, cube, net, all those things. If you click on this more, then you also have other things. And what is important many times is this polygon. So you can click on this and then you select this point. Okay. Now you drag up to here. Okay. Yes. Or just a second, because it is just a line, you don't require polygon. You can select this line segment. Okay. Select this line segment, then click this point and here. Okay. So now you can see that this line segment we have created. Okay. So after that, what we want to do, this is the one, you have a line segment. Then, as I said, after having a line segment, we want to rotate. So rotation is from 0 to 360 degrees. So we will create a point which is a useful for rotation. Okay. So for that, suppose I will say spin or rotation or whatever r is equal to, I'll just say starting from 0, then deg without any gap you can write, or you can just r equal to, then press enter, you will get other things. Okay. Then it starts from 0 degrees and the maximum one can have is 360 degrees. So we have created an r which you can slide it from 0 to 360 degrees. Now how we will use this one? We will use the command called surface. The moment once we type surface, different things it will come, expression, then parameters and so on. So here what we will do here is surface. Then we want to revolve around using this function which we have defined earlier here is f. That means our line we are going to make it round. Then we use the help of, take the help of this r, which is rotation, or you can write here also from 0 to 2 pi, whatever. Okay, that is also is allowed, right? Then after this, on which axis we want to rotate. So I'll write here about z axis because it is a height. So we want to rotate around z axis, right? So for that, you write here z, then capital A axis. This is the syntax for z axis. Now the moment you press enter, this vector is generated. Okay, fine. Now what we have to do, you go to this R and you start scrolling this. You can see here, the moment we started, now it is coming, right? So we are able to generate the surface using this line concept, okay, with the help of this surface one, right? If you decrease little bit, it will come like this, right? I hope whatever I have created here, things have been created here. If you want to change color, you just go here and right click it. This is, if you want, you can make it disappear. You see, if I click again, it's coming, right? So if it is not there, it was only one line was there. Now the surface is there. If you want, you can go to settings. Then you go to just simply color. Whichever color you want, you can take it. There's no problem. Okay. Click here. Fine. So you can see that wonderfully we have created a mug, right? And you can see in any direction. Okay. Yes. And if you want, you can move it somewhere here and there by shifting shift key. If you shift, and you can move it here at any place. If you want, you can put it. And if you shift and double key, then you can put it up or up, down like that. Okay. I'll go back to the original position. This is created, right? And this is the thing which one can start doing it. Now, so that means we have actually created one activity. After having an activity, how you can save this activity so that others can access it. So this is the algebra. This is the algebra, whatever you have here. If anyone put this one, they will get this. And whoever want to make changes, for example, here, instead of 2.5, if I make it 1.5, then you can see that shape is immediately changing, right? Okay. If I put it, suppose 0, instead of that, then what you get here is a cone, exactly a cone, right? Ice cream, you can call it ice cream cone. But right now I will change it to 2.5 because we are going to test it with our actual mug, whatever I have. Okay. Fine.
Dr. Surendra, you can add the base also so that you can get keep some water inside.
Yeah, but I want to show it. I am intentionally not adding base because while I am projecting to my augmented using augmented, they can see the base of my curve.
Sure, sure. Thanks.
Yeah. Yes. So anything one can add it. Suppose just here, for example, these are all the resources available. If you want to add some line or ray or midpoint, center, polygon, all these things one can use it. Then how you can use it, no need to explain somebody separately. Suppose if you click on this, for example, segment. So it says the moment if you say here, select 2 points or positions. Okay, if you take any 2 points selected on this, then automatically it joins a segment that I will explain many things while explaining that stereographic projection. Okay, so quickly this is ready. We will show it how we can save it and use it in that augmented reality. Okay, so if you go on top of this, if we go on top here, this GeoGebra, if you click on this, it says save, share. Okay, if you want, you can share it. So if I click on this share, if you click and give some title, okay, so suppose mug demo 3, and then you can click on save, and whatever options is available here, you can, yes, just that link, it was, you can click on share again. So here, for example, you can see that GeoGebra 3D, this, whoever you access this code, then they can, whoever having this one, for example, I'll copy it here and I will paste it in this here itself in chat box. Where is chat box? So whoever accessing, you can immediately there is chat box. Okay, where is chat box here? If I stop sharing, then yeah, now I can. Yes. So whoever want, you can click on this even from mobile. If you have a GeoGebra app, you can download it and you can directly see this one. Now I'll share my screen. I will show it from my iPad how we can project it using that augmented reality. So the only difference between augmented reality and this 3D setting are difference between morning lecture and now is that morning whatever professor has taken, he taken up to constructing these things. Then now it is an extension, and augmented reality is just using the app. We don't need to do anything. You just open that one. Okay. So let me share my screen this time. Whatever earlier it was there, I'll just try to open this. Yeah, it's opening now. I hope you can see my screen, right? Hello?
Yes, yes, go ahead.
Yes, yes. So here on this, so right now I'm trying to show it how it looks like as augmented reality. Once you open and from your Android mobile or iPad, at the bottom you will see this AR symbol here. So if you click on this AR, it is called augmented reality. So it asks for a better place to put it. Okay. So whatever this square is there, it says surface is detected. So I'll just tap here. Okay. So the moment I tap it, yes. I hope, can you see this one? Whatever we have constructed, this mug, you can see it from here.
Yes, beautiful. Go ahead.
Yes. So now we will see how whether it is whatever with measurements we have constructed, whether it fits to our model or not. So this is the mug which I have already here. Okay. So let me put it there and see whether it is having. So I'll put it here. Okay. I am not so good at putting things better. So is my this glass is visible?
Yes,
That
yes.
mug. And if you start, I think due to internet connectivity, there is a slight disturbance or slight connection delay. So you can see that almost it fitted. Okay. Now if I take it, so that as I said, because of my internet is little unstable, what I'm showing here is coming almost like after 1 minute. Okay, so as I said, you can try this. It is not at all a difficult one. Any model we can construct with the help of GeoGebra. Of course, depending on the shape, it requires some time, and of course, we require a lot of patience, and we want to learn how one can form different shapes. Okay, the second one which I will show you here is the which I like the most is how we can construct or explain things in better way, especially whenever there is a geometry is involved. Okay, so let me share this screen once again. So where are my resources? Yeah, so I'll go to this Riemann sphere. Yes. So now, can you see this this sphere?
Yeah, it is visible.
Yes. So if we want, we can zoom it. It is not a problem.
You can take little up. Yeah.
Yeah. So just one step I'll do. Okay. Why I like this such things is that many things I have added here. What we will do is we have taken a sphere. Sphere one can do it from easily by pointing out. You can even tell our students how one can construct a sphere. For example, to construct a sphere, what things are required. So you can see that if we have a center and a point, then a sphere can be constructed using this one. If you click here, then suppose select a center point and then point on the sphere, then it will be sphere is formed. So first thing is we have formed a sphere. Then after this, what I did here is this E, if you see here, this point E is 0, 0, 1, that north pole, whatever we are calling it. So this is the north pole here. Then if we want to explain to our students how we can have a projection from that point or any point from sphere to a point on our plane, okay, which is our complex plane, right? So you take any point on this complex plane, for example, this D I have taken here, which is a point on complex plane. Then from this north pole, we have drawn a line. So let me take, if we want to, how we can draw a line or line segment, you from go here and take this line segment. So for this, select 2 points. So I'll select this 1 point here and another point here. So you can see that this line is created, right? So once this line is created, we can explain that where this line or line segment is intersecting this sphere. You can see here, it is intersecting at this point and it is named as F, okay? So we can easily explain by saying that if we move this, so I'll go to this move and the moment I move this N here and there, then that point of intersection will change, okay? And not only that, if you take a point which is below to this sphere from that complex plane, where that will be mapped to in that sphere is that 1 point also I have shown here. For example, this room is making it. Yeah. So this line, whatever, if we see this point of contact, this, when I join E and this point, it is coming here, okay, below. Now in this direction, you can see it. So the whatever you are having here, that is below part of that sphere. So that will be touching here. So that entire circle, whatever plane it is intersecting this sphere, that will be projected to the this lower part of the sphere, okay. Then saying, see, for example, if I move this point, you can see here, however, I am moving this point, sorry.
Dr. Surendra, you are on mute. Dr. Surendra?
Yes, yes.
Yeah. Okay.
So now you can see that these points, for example, if you want to explain the neighborhood around infinity. So how these points are mapped. First of all, if you understood this concept, only 1 point on this sphere is not mapped to any point on the complex plane. That one can easily guess from here, because whenever we want to draw a line segment, we require at least 2 different points. So for this E, whatever we are having this one, if at all we want to project this E to any point on this complex plane, then we require 1 more point, right? But with that point is already mapped. So this E cannot be mapped to any point in this complex plane. So when we talk about Riemann sphere or stereographic projection, that is the reason this E is mapped to, this E is mapped to something called, we will call it as point at infinity. Then we'll talk about whichever points are near to this E, that we will try to say that they are.
Surendra, your screen is not visible. Are you sharing?
Oh, one second. Because in between I was logged out for a second, I think because of that. Yeah, is it visible now?
It's coming up. Yes.
Yes. So what I'm saying is that this sphere, only this one point is left out. It is not mapped to any point in this complex plane. So we talk about extended one, then we take this point infinity. And then how we define the points near to this ER, we will call it as points near to infinity. That is the how we define neighborhood of infinity, right? So how they are looking and where, what are the points which are available in neighborhood of infinity, you can understand this from this picture. The moment you go far away from this sphere, then those points are very, very close to the sea. By imagining this, you can rotate here and you can check this one. And in this way, it is, because if I go very deep, it will be a little problem. But many concepts, especially involves geometric things, we can explain immediately, and all the things we can use it here. For example, we can easily find out point of intersection of a plane and a sphere, or any two surfaces, that we can use it here. Polygon, which we have already explained. Solids one can construct easily. We can generate a circle. All the things are available which are ready made. If we just start using it, algebra will be automatically created for this. Okay, so exactly it is 2:40. Okay, maybe I'll stop here and I will ask for some questions if they have. What I have shown already here is how you can, after constructing, how you can generate your resource, that you can, the moment you click on this save. So whatever you did it, you just click on save. After log into your account, you click on this save button, then you give some title. After that, you click save. So once the moment you click on save, that will be saved, right? And it will be available as a resource. If I click on this, my resources, now you can see that whatever we have just created, that resource is available here. So I can, anyone, whoever access these things, if suppose as a resource activity, if you click on this, then it says who is the author and what is the title, and this is the algebra, one can have it. Okay, so in this way one can create, everyone whoever participating in this conference, you can all create whichever visualization you are thinking in your mind. Start with small things, create some resources so that you get some energy or interest to create bigger and bigger things. Okay. Yes, sir.
Okay, thank you, Surendra. So we can take a few questions.
Yes.
Yeah, so in case you have questions, please either you can click on raise hand or you can put it in the chat box.
Somebody is asking once again how to bring it in photos. What is meant by bring it in photos?
I think what she means is the augmented reality, I think.
Augmented reality.
If I understand it correctly.
Okay. So, see, for example, this one is there, which we have created. After that, we want to show it to students or anywhere in augmented reality. What you have to do is you have to find this resource. So let me share once again my laptop, this, because I will also show you what are all different resources. See, main important thing is if you want to learn first thing, you can explore already whichever is available. That may be helpful, and many people who are experts in the field, they might have designed far better than us. So I will show you that where you can find the resources from your app. Okay, then that augmented reality, just for a minute I will show it again. So this I'll So if you see here my screen, just I'll clear up. Okay. Now, if you click on these three dots here, you will find that there is an open symbol. Okay. In iPad, this will be named as open. If you see in Android, it will be something like search or open name. Okay, so you click on this open. Once we click on this open, then what we get here is lot of resources which are currently available. Yeah, it is opening. Yes. Okay, so you can see that, for example, if you click this one, then immediately it will come and you can show that. So whatever is available, I will show that. Okay, so this augmented reality, I am able to show this picture to my students. Okay, I can rotate it, and you can see if you click on these three horizontal dots on above, sorry, this one here, you will have options and open and close. You can see here. As I said, my internet, because of net less, I am not able to synchronize my tab here, but you can see it. These are all slides. So once you open and close, you will try to understand how this one. Okay, this is already designed. You can take the help of height, width. You can decrease, right? And yeah. Now you can see that this sphere, whichever you are talking about, is, you can rotate it. Okay, or you go here and find again open. For example, you type here Riemann sphere, you want to know it. Okay, anything, just start typing. If at all it is there, you will find lots of sources available already, and anyone you can take and you can start explaining or exploring yourself. Okay, for example, here definition of the double integral, it is a beautiful one. You can start. Yeah, you can see that there is a definition of the double integral. It is already available. If you just press it, and you can try to explore things, and it is a nice thing. And if you want, you can explain to students. Definitely students will like it. This augmented reality is useful in two things. One, visually it appears very good, and in front of you, you are actually seeing that object virtually. And the third one, or second one, is you can test the whatever model we have designed, whether it is actually fitting or not. Any things need to be corrected. Somebody said iPhone. I don't have, I mean, iPhone or iPad. It works in Android phones also. Only few phones it may not be supported. But the thing is, other than augmented reality, it actually 3D image will be available. It will be visible on your phone. You can share your screen. It will be visible as it is. Just like on a computer, how it will be visible. The same way you can access, you can explore things. Only augmented reality may not be available on all Android phones. At least you require Android 8 and above or something like that. Yes.
Okay, I think Shredra, there is one question somebody has asked, Mr. Tejas, how to download GIF file of moving surface. So do you want to comment on that?
Yeah, this when you go to whatever you have created, if you go to this, here there will be an option called export image. So once you click on this export image, then we can download that image. It may be as a PNG file, and if at all as a GIF, maybe here download as, yeah, here if you download as, if you click, then it is available as a GeoGebra file or HTML, but not GIF. I didn't find that one, so I can't answer it. Ajit, if you know, you can, or somebody know, then they can say it.
Yeah, I mean, I think what he means is animation.
Yeah.
Whether it can be saved.
If there is an animation, then only you can make a GIF file. Otherwise, you can't make a GIF file.
Yeah.
So that slider which is animating, then you click on that, and then there is a GIF animation possible. Not always.
Okay.
Right. So
yeah, I think we can close.
if there are no questions, let us thank once again Dr. Reddy for wonderful presentation on this 3D calculator and augmented geometry. And you can see here that he took an example of very simple rotation of a line to a concept which is stereographic projection. Generally, the student learn in MSc classes usually. So you can see here the variety of the applications that one can do, starting from very school mathematics to undergraduate and postgraduate mathematics. So thank you, Dr. Surendra, once again.
Thank you, sir. And thanks to Rana, sir. Especially asked me after that, I explored many things. And definitely I will be exploring again and again. Yes.
Okay. Thank you, Surendra, for putting in this effort and helping in many other things.
Yes.
I won't say it publicly. Thank you.
Yes, sir. Yes. Yes.
So we close this session and we come back in about 12 minutes for the next session. Okay. So there's a break for 12 minutes and we come back. Thank you. Julia. Hello.
Hi.
Hi. Would you like to test screen sharing or something?
Yes, please.
Yeah.
I
So
will try if everything is working.
yeah. Please start sharing your screen, the title, and that will be okay.
So, can you see my screen?
Oh yes, beautiful. Yes, we can see it.
Okay, perfect.
Yeah. So you can leave it on.
Yeah.
वीडियो में तो सर को पूछे कि सर एम आई वीडियो में बुड्ढा क्या बोला यार यू आर वेरी ब्यूटीफुल
So we have some few minutes. We just have 1 minute to go. So how cold is the water in Austria?
Yeah, at the moment it's a bit colder. Last week we almost had some spring weather that was very nice, but yeah, last week it was snowing a bit, so we have to wait a bit for the spring to come back.
Okay.
How is it in India?
Well, it's around 32. Reasonably hot.
I'm also looking forward to summer to have such temperatures back here in Austria.
Yeah, right. Australia being more closer to the Alps, I think it's more colder there. Yeah, it's time to begin the lecture, afternoon 3 o'clock lecture. We have with us Julia Wolfinger. She is from the GeoGebra team. At present, she is, I think, based at Linz, Austria. And in case, Julia, would you like to say something more about yourself? Say it, and then you can start your presentation. So looking forward to GeoGebra, the present and the future. Please.
Thank you. I'm very happy to be here today and that I'm allowed to show you what we are working on in the last time and also give you some insights in the future. So what we are planning to do and also on what we are working at the moment. Yeah, I'm Julia. I'm working at GeoGebra since almost 3 years, and there I'm leading the GeoGebra community team. I just want to give you a quick insight what we are doing at GeoGebra. So my team, for example, takes care of the user support. So if you have any questions, any wishes, any ideas, or any problems, you're always welcome to contact us at support@geogebra.org. So my team is taking care of all our requests, and yeah, we try to help you to solve all the problems. Then we also take care of resources. So we're creating resources. We're also sharing nice resources. We take care of social media. So when you follow us on social media, you will always see the latest news. So if there are some new features or some app or some great events, you will get lots of information there. We also write tutorials. So for every app and for every feature, we have instructions on our website. So my team is therefore writing some tutorials. I will also share them with you at the end of the presentation. And we also take care of the community. So I'm really loving giving talks or giving workshops to our community to share our work and to share what is going on in our world. Yeah, I will share the slides with you afterwards in the chat, so you will get all the links that I have here in my presentation, so you don't have to write them down. Yeah, what I want to do today, or what I would like to show you today, are some new things on the website, and later I will also show you one of our newest apps. But I will start with the website. On the website, we had a really nice project last summer. After GeoGebra Classroom was released, we started on a project on open educational resources. We wanted to provide teachers resources for teaching so that these resources also fit a curriculum. Therefore, we had a closer look at the illustrative mathematics curriculum. So IM is a highly acclaimed content and practice standard focused curriculum where students learn to understand and to make connections between concepts and procedures. And GeoGebra made a completely digital version out of this curriculum for free. Yeah, what does completely digitally mean? That means that we include lots of different additional interactive activities. I will show you in a minute how that looks like. So you can use these resources in every kind of teaching setting. So it doesn't matter if you're teaching live in class with your students, or maybe you're separated and you are teaching online because the students are at home, or even if you're using a hybrid connection. So everything is possible with the curriculum. And if you're using it with GeoGebra Classroom, you're also able to monitor the work of your students. So you can help students when you see that they're struggling at some tasks, or you can also have classroom discussions. Yeah, it's possible to use Classroom on every device. So it doesn't matter if you're working on a tablet, on a phone, or on your computer. And now I'm going to show you how this curriculum looks like, and also how you can use this curriculum with GeoGebra Classroom. So on our website, when you enter geogebra.org/im, you will find here our curriculum. As you can see here, we have done this already for middle school. We started last summer with the middle school curriculum and already finished that. And as we get so much good feedback from teachers, and they also keep asking if we can do the same for the middle school, for the high school, we also started in autumn to work on the high school curriculum. So high school curriculum is still in progress. But the first units are already done, but the other units will come. So stay tuned, and you will find the units here linked as soon as they are ready. Yeah, but you can use this curriculum with GeoGebra Classroom, as I mentioned before. Therefore, you will have here a short instruction where you can find a short demo how to do that. I will also show you that in a minute. And you can also use it with Google Classroom. Therefore, you will also find a short instruction here. Yeah, let's have a closer look at the middle school curriculum. So in the middle school curriculum, in the next step, I could choose the grade. So let's assume that we are teaching in grade 6. After I selected the grade level, I can also select the units. So let's have a look at unit 1. So now I have here all the exercises of unit 1. So you can see here the titles, and we always have a teacher resource and a student resource. So when we click on the teacher resource, we will get to the IM page. We get lots of background information for the teacher. So the teacher now gets here information what should be important for the preparation. And when we go back here, sorry, that was the wrong tab. Yeah. We also have the student resource. So when I click on the student resource, then I'm here at a GeoGebra book. So in this GeoGebra book, we have now this interactive version of the curriculum. So we have a lesson component and a practice component. So as you can see here, we took the curriculum and made a digitally version. So for example, here we have an open question. Then, for example, for this open question, we have an applet where students, for example, could add segments or something like that, just to visualize how to separate these objects. So that should be a help for solving the task above. So there are lots of different activities, and also in the breakdance component, we added some applets, which helps students to solve tasks. We have some questions. Sorry, could you hear me before? Because I just was muted now.
Yeah, we can hear you.
Okay, great. So we have here an interactive curriculum, and if we would like to share this with our students, we can create a class. So if you want to share that in GeoGebra Classroom, you just have to click here to create a class. And here you can decide, do you want to share both the lesson component and the practice component? Then you would share the book. Or do you only want to share the practice, for example? Because I'm now at the practice side where I clicked the create class button, so I'm also allowed to only use the practice component. So I will just use this activity. I'll click on create. And now here I'm in a virtual class. So I invite you all to join me in this class and to get in the perspective of a student. So you will see by both views, you will see the teacher view on my screen, and on your screen, you would also see the student's view. Therefore, I'm sending a link in the chat. So when you go to this link, you will be directly in the class. You just have to enter your name. So there are two possibilities to join a class. You can either just enter your name and join as a guest, or you can use your GeoGebra profile and log in with your profile. The benefit when you log in with your profile is that your work will also be saved for you. So it will not only be saved for the teacher, it will also be saved for you. When you're not logged in, it will be saved for the teacher, but you can't come back and continue later working on that. So this is the difference between logging in and joining as a guest. So as you can see here, I'm getting some students in my class. So for joining a class as a student, there are also two possibilities. So as a teacher, I can send this link like I did before in the chat, but it would also be possible that my students are entering a code. So when the students go to geogebra.org/classroom, they can also enter this code. So that would be a second possibility. Yeah, while I'm waiting, maybe some more students will join. I show you another feature. So when you click on the share button in the right upper corner, you're also able to add a co-teacher. Maybe you are teaching with a colleague, and then the colleague also would like to see all the results of the students. Then it would be possible to add a second teacher. Therefore, you will need the email address or the GeoGebra username. So for teachers, it's always necessary to have a GeoGebra account to create a class. So now we can see here, I already have lots of students here in my class, and you can see here that I have different previews. So you can also see that these previews are changing. So I will get real updates on what the students are doing. So if the student is drawing something or writing something, I get here an update in real time. I also see in these thumbnails on which tasks the students are at the moment working. So I see all the students are already working on task 1. If someone of the students would change to or go forward to task 2, I would get here an update. So I can also see if students didn't start it already. And I could also have a closer look at the results of a student. For example, when I'm clicking on a student card, I see the same like the student does. So for example, I can see here now all the results of the student, and I can have a closer look at that. I would also have the possibility maybe to hide the names. That would be very important when I would like to discuss different results with the students. For example, when I'm doing online teaching and I'm connected with my students via Zoom or any other video conference tool, I could have online discussions when I share my screen, but then maybe it's important to hide the names so that the students are not feeling bad when they made a wrong solution and I'm showing different solutions. So nobody would know who is working on which task, so that's anonymized. Of course, I can click again, show names, and then I would know who is doing what. So that's the class overview page where I see how many tasks did the students already started, on which task are they already working, and how many students are in my class. Then we also have the task overview. So here we get a summary of every task. I see 20 out of 41 students already started with task 1. I also see nobody started already with task 3. So here I have a good overview how many tasks have already been started. And of course, I could also have a closer look at the different tasks. For example, here we had this task where you should calculate the area. For example, I see here all the different answers from my students. And also these files get a live update. So if anyone is changing something, I would get a live update. Yeah, same for task 2. There we also had an applet. So we can also see here different ways how to solve the task. Task 3 was an open question. So you can see here that we also see here the answers of the students. So if someone is starting typing, here would appear a next card. And even if the students are changing, like here, when the students are changing their answers, you will also get a live update. Of course, if the answer would be much longer than only this card, you can also click on there to get details view. What else did we have? Here we also have this applets, and we also had a multiple choice question. Maybe you all go to task 5 and just change random your answers, because then we will see here this nice feature that these answers are also updating in real time. So as soon as a student is changing the answer, you can see here now that these graphs is changing in real time. Maybe here it's also good to mention that we have a pause feature. So when I click on pause, you're all not able to continue on working on the task. So this feature is, for example, helpful when you are discussing the results of a multiple choice question, because here you can also show the correct answer. And maybe before I choose correct answer, it would be nice to pause the class, because otherwise everyone would jump to the correct answer. And after I was talking about that, I could resume the class. As a teacher, I also see which student choose which answer. So I also got this information. And of course, I could also hide the right answer. So there are these 3 types. You could have an applet, or an open question, or a multiple question. So these are the 3 task types in GeoGebra Classroom, and all the IM curriculum activities include such task elements, so that you can really use it in every setting. It doesn't matter if you're at school or if the students at home, because here you can have a good overview what the students are doing, if they need help at some place, and yeah, you can help them. Yeah, that was GeoGebra Classroom and the IM curriculum. And as I mentioned before, in the next time, we will also have the high school curriculum. Yeah, then I would like to give you an outlook what is coming soon for GeoGebra Classroom. We are working on an equation editor for the student input. So at the moment, when you have an open question, there is no equation editor. So you can use your keyboard and enter the question, but especially for math or maybe for physics, it would be also nice to have all the math symbols or to enter nice equations. Therefore, we are working on an equation editor, which will be added to the open answers so that students can write answers in a nice math form. And one big feature and very exciting feature that we will add are collaborative whiteboards. So it would be possible that there's also group work in GeoGebra Classroom. So the teacher will have the possibility to choose if there should be a single work or if there should be group work. And then, as you can see here in the preview at the slides, so that are our drafts, we will have a group that is working on a whiteboard and they could work together. So for example, the students one is writing an equation, also the other students in this group will see the equation. And therefore, for this whiteboard, we will use GeoGebra notes. Maybe some of them already know GeoGebra notes. GeoGebra notes is an interactive whiteboard from GeoGebra. So you have there lots of different possibilities. So you can use all the tools that you're used to use from a whiteboard, like a pen tool, a highlighter, and an eraser. You also can use lots of different features. You can also embed images, pictures, the GeoGebra graphing calculator, the GeoGebra CAS calculator, videos, websites. So you have lots of different possibilities. And there we are also working to add a mind map feature. So if students are working together on this collaborative whiteboard, they would have lots of possibilities. And for the teacher, it will be also possible to go through different groups to help the students to have a look what are the students doing. And for this feature, we will also add a chat to GeoGebra Classroom so that students in a group can communicate with each other, and also that the teacher can reach the students so that he or she could give them some tips or tell them there are only 5 minutes left or something like that. So this will be a really great feature that will be added to GeoGebra Classroom. Last week, we already tried the first prototype in a team meeting, and that was very excited. So I'm really looking forward when this will be released and all of you can also use that feature. Yeah, that was a quick outlook what is coming for GeoGebra Classroom. I also want to show you what else did we do on the website. So in last spring, we also made a resource collection. So as you may know, there are lots of great resources at the GeoGebra page, and we would like to make it easier for teachers to find really good stuff. So therefore, we created some collections. So you will find these collections on our front page. So here you can see we have a collection for elementary school resources and also for high school and middle school. So when you click on such a collection, you will find here that we collected the resources in grade levels. So for example, let's have a look at K2 geometry, and there we link to a GeoGebra book where we collect good stuff from different authors. So there are lots of different resources, and teacher can have a look if there's something that they would like to do with the students. And lots of these activities also include auto-checking, which is also nice when the students are maybe learning in distance, so learning at home, that they also get automatically feedback if they're doing right or wrong. So you can find lots of these resources on our front page for the different grade levels for elementary school, middle and high school. So feel free to just have a look there if there's something for you and your students. And something else what we did is the remote learning class templates. So we also created some templates that could be used in GeoGebra Classroom. So for example, at the beginning, we here have some mood checks. So for example, when you are teaching online and your students at home, you do not really see their faces, you don't know, are they tired, are they really active? So maybe you can add such a short check at the beginning of the class to get the feeling, are they very positive and energy, or is my class a bit tired? And so maybe you can also have a bit of a social part in your classes. So it's easy to add these activities to all our other activities. So that would be some different mood checks, or also if the students are showing thumbs ups or thumbs downs, how they are feeling. Or you can also let them draw the stress level, that you can see, okay, how stressed are they? Is there lots of other stuff to do in the other subjects or something like that? Yeah, beside of these mood checks, there are much more, as you can see here. We also have some different whiteboards and also the GeoGebra apps. And here we also have some other nice templates, like, for example, when you're teaching and you would need a clock, there would be a clock template, some coins, or a ruler maybe is also helpful. So you have lots of stuff here that you can include to your activities. And how to include to your activities, therefore you will also find here a silent demo where we show how to do that. So the link to all these resources is on my slides. So yeah, so that also were two projects we had over the last time to make it easier for teachers to find such resources. Yeah, okay, so that were the news from the website. Now I would like to continue with the GeoGebra apps. Last summer, we released the GeoGebra Street Calculator. The GeoGebra Street Calculator should be the successor of our good old Classic app, because in Classic we have the problem that you can't use it on mobile phones, and we think it's also very important that you can use the offline apps on the mobile phones, because lots of students would like to work on the mobile phones, and also that it's possible to have on the mobile devices an exam mode. So that's something that's definitely possible with the new Suite app. So you can download it on every device, you can use it offline, and you can also use it in exam mode. Yeah, at the moment, we have the graphic calculator, the geometry app, the CAS app, and the 3D app combined in the Suite calculator. So you may know all these apps. They are now combined in the new Suite app. I will show you in a minute how that looks like. Yeah, maybe before I will give you a quick overview of our apps. So may you know we have lots of different apps, and if you wonder which app is the best for you. So the reason why we offer different apps is that in different regions, there are different rules what is allowed for exams. So not in every region, for example, it's allowed to have symbolic calculations in the exams so that they are done with technology. And therefore we offer different apps so that everyone can have a look what's allowed in my region, what can I do with technology for exams, and then you can choose the right app. In Austria, for example, we are quite open. We are allowed to use everything. So our final exams are at the moment done with Classic, but in the future, I think they will be done with the Suite app. So you can have a look at this table. You will find it in my slides, and you will find it in every tutorial at the beginning, and you can decide which app is perfect for you and your students. And as you can see here, the Suite app includes almost all features of the other apps except of the probability calculator and the spreadsheet, but both of them will be added during the next school year. So after the next school year, it should be possible that the Suite app includes all the great features that we already have in the Classic app. And additionally, you can use it on mobile phones in exam mode. Yeah, and now I would like to show you a short demo of the Suite app. Therefore, I'm sharing the screen of my mobile phone. So here, now you can see the Suite app. So it looks like the graphing app. That's we are now in the graphing perspective. So in the Suite app, in the menu, you can choose which calculator you are using. You have here the switch calculator, and when you click on that, you can choose in which perspective you would like to work. So I start in graphing. So I have here the graphing calculator. The graphing calculator has the algebra view, a tools view, and a tables view. And I just want to give you a short example how you can use the graphing calculator. So the graphing calculator is great for functions. So I'm now adding a linear function with two parameters. So ax plus b, and as soon as I click, oops, there was something wrong. So let's start again. Ax plus b. As soon as I click enter, I get here two sliders. So I have a linear function with two sliders. So I'm also able to show the sliders here in the graphics view. I can move the sliders around. So when I click on this bubble here, I can decide if the slider should be shown or not shown in the graphics view. So now the sliders are shown. Then, for example, I could add a second function like x squared. Then let's have a look at the tools view. In the tools view, I could, for example, use the intersect tool. When I use the intersect tool, I just have to click on both functions and I now get the intersection points. When I then choose again the move tool and I move the sliders, you can see that's all interactive. So when I change the parameters of the linear function, of course, also the intersection points change. When I go to the algebra view, I can see now here that also here the information of the intersection point is saved. And when I go to the table view, that would be empty now, but it's possible to add a function to the table view. For example, when I have here my function, I can click on the three-dot menu and you will find the entry table of values. When I click on that, I can choose the start value, the end value, and also the steps. Then I confirm with OK. And you see now here, I have a table of values. And if I change, for example, the value of the linear function, you can see that there are also changes in the table view. So that's typically for all GeoGebra apps that all views are connected dynamically. Okay, so then let's have a look at another perspective. Let's continue with geometry. For example, in geometry, I have all the geometry tools. I'm now creating a polygon and a segment. And then you can see here, I have more tools. So some construction tools, some measurement tools, and also some transformation tools. So for example, I could reflect these about my segment. And when I choose again the move tool, you can see that everything is connected. So that would be the geometry perspective. Then let's have a look what's left. We also have the CAS perspective. So for example, in CAS, you can do symbolic calculations. You could also have a look at integrals or calculate integrals and derivatives. So I have here my function x squared. I label the function so that it has a name. And then I could use the command integral. Of f to create the integral. As you can see here, I also get a slider. So to explore all the integrals with the constant, and I could also explore the derivatives. Therefore, you can see here at the keyboard, there are also two keys. There is a key for integral and a key for derivatives. So you do not have to always enter the whole command. So I would also see the derivatives. So that's also something that is quite nice in the CAS perspective. And as you can see here, there would also be the table view. So it would also be possible to add a function to the table view. Yeah, then there's one perspective left. So it's the 3D calculator. So as you can see here, I do not have to leave the app. Every perspectives are included in one app. And for the 3D calculator, I would also like to show a new feature. In the talk before, we already saw some great AR demos. I would like to show a new feature in AR. So the 3D calculator or the 3D perspective also includes AR here in the Suite app. So for AR, you are able to make some models in the real world, and I will show you that here. So let's start again because it didn't fit exactly my table. So first have to find a surface. Now I have here the coordinate plane on my table, and you can see here that I have here a ratio 1 to 2 centimeters. That's also something we released last year. So you are now able to change the ratio between the real world and the GeoGebra coordinate system. So, and if I change the ratio to 1 to 1, I could use real measurements from the model and see the results. So for example, I'm now modeling this box. So now it's not working. I should just restart. Let's try again. So let's change the ratio to 1 to 1. And I will use the polygon tool. Now it works. So you can see here now a point and a circle. And I can use that one to mark all the edges to mark my area. So I'm going around, and then I will choose the first point again. And then I could use the extrude to prism tool to raise it to the right height. So now I would make a model out of my box. And now I could use measurement tools. So we have here different measurement tools. For example, when I choose the volume tool and I click on the box, I directly get the model the volume of the box. Or I could also have a look at some distances. So you can see here the distance. So you have lots of different possibilities to measure your model. And therefore it's important that the ratio is 1 to 1. Okay, so that was the suite calculator. So you can see you have lots of possibilities. At the moment, it's not possible to download every single app because now you can all use all these great all these great apps in one app. So it's enough to download the suite calculator. Yeah, I already mentioned that we will add the spreadsheets and the view and the probability calculator. And at the moment, we're also working on an offline version for Mac OS and Windows. At the moment, for the computer, we only have the online version, but that will be done very, very soon so that you can also use the exam mode on the computer. Yeah, as I mentioned before, I would like to show with you the tutorials. So we have a tutorial for GeoGebra Classroom. There you will find all the information that I give you today in a written form so that you can go through it. And I will also share the tutorial to the suite calculator. You will find lots of different examples and also instructions how to use it. And I also added here the link to our further tutorials. So if you're interested in other apps, for example, like Notes, unfortunately, I do not have time to show that today, but maybe sometime else. But you would also find instruction how to use GeoGebra Notes here. Yeah, and I also invite you all to stay tuned to join our newsletter. So if there are new features, we are sending out a newsletter. And if you are interested, we are very happy if you join to this list. I will now send the link to the chat. So I invite you all to subscribe to that one. So now you have the link. The first link is for the presentation and the second one is for the newsletter. So if you sign up, we will give you all the nice information we will keep you up to date what is coming. For example, of course, you will get an email as soon as the multi-user version is ready. And yeah, so that you don't miss this information. Yeah, that was all from my side. If you have any questions, ideas, wishes, of course, I'm now here ready for questions. And if you have afterwards any questions, feel free to write anytime at support@geogebra.org.
Thank you, Julia, for giving the insight for the future of GeoGebra. And if audience have some questions to ask, clarifications, suggestions, what could be or a wish list for GeoGebra team, then please come over. Anybody has a in the meantime, let people think about questions. I just want to ask you, for the equation editor, would you have the LaTeX port?
For what? Sorry? LaTeX port?
LaTeX.
LaTeX?
Yep.
For classroom, or for what do you mean?
No, in that equation editor that you said we are planning, right? Equation editor, equations editor.
Equations editor.
Yeah. Will that have a LaTeX port also?
Good question. I don't know. So I haven't seen the equations editor at the moment, but I will ask. I will ask and let you know.
Yeah, and make it my wish list. Also, they should have it, because those who already know LaTeX, they don't have to worry about going to superscript, subscript, and all that kind of a thing.
Okay.
Yeah, it will be.
Thank you. I will ask, and otherwise it is on the wish list.
Another thing which I have found missing in most of the GeoGebra things is, if I copy from somewhere, say LaTeX formula, I'm not able to paste it in the text for in the text field of, say, Classic 5 or anywhere. I have to retype the whole thing.
Okay.
So that is a big sort of a bit nuisance, because in my lesson I would like to take an equation which I have typed to the text of say Classic app. So that sport both ways, copying and pasting for LaTeX should be.
Okay. I made a note about that too.
Okay, thank you. Anybody else has a question? Will it be same as equation editor available MS Office? Somebody has put a question saying, will the equations editor be similar to the one available for Microsoft Office?
I don't know how it will look exactly, but I know that would be not the same, because we are creating an own one. But yeah, how it really looks like in detail, I don't know at the moment.
Yeah, but the graph, when you showed a snapshot of that, that looked like something putting in the picture form, like superscript goes up, you have to move it up, type it, which is same as almost Microsoft. Yeah. Anybody else has a question?
Can I ask something? Hi.
Yeah.
So this is Makrand. I am like one of the organizers. So I'll just go ahead. So do we have a tool which like to illustrate topological things which we do usually in undergrad? For example, if you have a square and you identify the opposite sides, you get a cylinder. Right? So like maybe something like that, just to visualize some topological things.
Did you get the question, Julia?
Not really. So the sound was not really.
No, the question is, in a 2D, you have a piece of paper. In 2 dimensions, you have a piece of paper, ordinary piece of paper. Supposing you take the opposite ends, edges of the opposite, and join them and glue them together, you'll get a cylinder. So is that kind of a thing possible in GeoGebra? Or so that is called cutting and pasting, is an important subject in mathematics. So maybe if that is a kind of tool possible, that I select one edge, I select another edge, and I say join, it should join and give me 3D kind of a thing.
Okay. No, I think there's no tool for that. There's just a tool for the net. So if you have a solid and then click on the solid, you automatically get the net. But in the other way, it's not possible that you have a 2D feature and then make a 3D out of that. So I don't think that we have something like that.
That tool of surfaces of revolution in 3D, that is you're taking a segment rotating. So that is a 2D.
Yeah.
Right, but that is rotation. So what he is asking is pasting and sort of. So
I will make a note for the wish list.
Yeah,
exactly. I was just wondering if that can be used, because that is something which I think is it becomes very good visualization if that can be done. As in when students usually are first introduced to topology or something like that, which they usually learn in undergrad. But then it is difficult to do this in real thing. Like with a software, we can do a lot more. So I was just wondering if there is something like that, or if is there any plan to do that, or whether it can be done with the available features. So
I will put it
just
on the
had-
list for future feature discussions. So we always have some discussions where we can collect the feedback from the community, and there we'll mention it.
Yeah. For example, a Mobius strip can also be created like that. Like a Mobius strip is usually more popular than the other things.
So cutting and pasting is basically what you.
Okay, thank you. Yeah.
Right.
Okay, thank you. Yeah.
Anybody else would like to ask a question or make a wish list, please? GeoGebra should have this in the near future. Anybody? Any suggestions? No? No wish list? Already learning GeoGebra is a big task because there are so many nice features available in GeoGebra. You keep on learning, and there's no end to it. Right. So using the already existing ones in the classroom is one challenge in some sense for teachers. Right. Yes. No, I think it's time for you to thank formally again, Julia. And,
Thank you too for having me here. It was a pleasure to join your conference.
So hope to see you sometime in Linz again. I was there about 10 years back for the first GeoGebra conference.
Yeah.
Okay. So thanks a lot again and take care.
Thank you too. You too. Goodbye.
Bye. Yeah. So next session will be at 4 o'clock. So we have a time for about 15 minutes break. So
Hello, sir.
hello. Hello.
Dr. Revati is here. Can you make her co-host?
Yeah, I just messaged her that join. It's okay. I'll do that.
Yeah, she is here. Yeah.
Okay. Good. Janaki,
Yes, sir. Right. I'm here. Yes.
would you like to share the screen and
Yes. Keep it ready. Yes, sure.
please do that.
Yeah.
Yeah, you can put your first screen and then.
Okay.
Hello, Revati.
Hello, Revati.
Can't hear. Your mic is probably audio.
Yeah. So I should maximize the yeah. So if I just need to move to the GeoGebra, I'll minimize this and open the GeoGebra screen, right? Is it visible, sir?
Let me just.
Is it
Yeah,
GeoGebra?
yes, the GeoGebra.
Okay. And the slide also?
Yes.
Okay, fine. Thank you.
Revati, is your mic on?
Hello?
Yes.
Yeah, now we can move.
We can hear.
No, I am unmuted. Am I not audible?
You are not audible earlier.
Now you are.
Yes, close your phone and let us see now. So, how was your flight yesterday? Okay, very much delayed.
Yeah, very high. Yeah, that was the whole issue.
Okay.
I was in Gujarat and I had to come back.
Okay, fine. So you are audible now. Fine.
Oh, okay, okay.
I was just testing whether audible.
Yeah.
Okay. So we have got around 5 minutes more to start. Or
yeah.
Whichever watch you want to keep it. Mine is 5. I don't know Janaki is how much and.
Yes, my 5 minutes.
Minutes. So 5 minutes.
Basically, let me know when I have sort of 15 minutes left. If it's possible, you just interrupt me and let me know.
Yeah, Revati, you are the chair, so you will intimate her.
Yeah, assume she's
yeah.
Okay. So I will disappear. Let Revati take over after 5 minutes.
Yeah.
I'll be here only. I disappear virtually.
Yes, I can see that you are there throughout. So how are you, Revati? It's been a while.
Yeah, okay. I'm doing good.
I missed your inputs for the panel discussion.
Oh, you couldn't make it, is it? Oh, because you had to go. Okay.
Yeah, she was not back in time. The flight was delayed.
Oh.
Yeah. So 3 more minutes to go.
Yeah. Yeah.
One more minute, I think. Can we start? Can we start?
Yes, please go ahead.
Can I start?
Yes, please go ahead. You are the chair.
Yeah. We have with us today Dr. Janaki Ghosh, who is a faculty in the Department of Elementary Education, Lady Shriram College, University of Delhi, where she teaches courses on mathematics education. Her primary areas of interest are in the use of technology in mathematics education, professional development of mathematics teachers, and popularization of mathematics. She has published articles in the proceedings of conferences as well as international journals. She has authored books for school children. She has spoken in several national and international conferences. So we are very fortunate to have a person like Janaki Ghosh making a presentation to us today. And I'm sure all of us will benefit deeply from her presentation. So wishing Janaki a very enjoyable talk and wish all of you a memorable presentation. Welcome to the session by Dr. Janaki Ghosh on conjecture making and proof in a dynamic geometry environment.
Thank you so much,
Welcome,
Revati.
Dr. Janaki.
Thank you for that very kind introduction. Am I clearly audible?
Yeah.
Okay.
Yeah.
So thank you to the organizers. Thank you, Professor Rana, for having me. In fact, I am kind of humbled because I have seen such wonderful presentations in this conference till now. And mine is going to be a little more on the basic side because I'm not going to be able to share too many the grand features of GeoGebra, but maybe how the basic tools can be used by children to develop their mathematical thinking. And in that regard, I chose the topic of conjecture making and proof in a dynamic geometry environment. So first, there will be a brief overview of, very briefly, I'll just touch upon the use of technology in math education, but focus more on the role of dynamic geometry software in teaching and learning of mathematics, especially teaching of proof, because one of the fundamental goals of teaching mathematics is to enable students to produce correct arguments, do meaningful justification, and lead them on to proof and writing proof, maybe to some extent. And hopefully I'll be able to share some examples of students' work in some of the studies that I have done and other studies as well. So the recommendations of the the position paper of the teaching of mathematics of the National Curriculum Framework 2005, of course, had said that, school mathematics needs to be activity oriented and accessible and affordable by all. But it also made a very important recommendation, which is even very, very relevant today after 16 years since the document was prepared. The shift from content to processes, that is, content is is already there, and there's nothing wrong with the content that we are teaching to our students. But probably the focus should be more on the processes of formal problem solving, estimation, approximation, visualization. And here it mentions reasoning and proof as one of the critical processes of mathematics learning. And here is where I feel explorations and investigatory problems involving dynamic geometry software can have great relevance. And the whole point of using technology is that, it takes over computations. So children are reduced of the cognitive load. And also we have seen even in the previous presentations, how we can explore concepts using multiple representations, that is numerical, graphical, and symbolic. Also, the position paper talks about proof at a point and says proof is important, but equating proof with deduction as done in schools often does violence to the notion. Sometimes a picture suffices as a proof. A construction proves a claim rigorously. The social notion of proof as a process that convinces a skeptical adversary is important for the practice of mathematics. And then what it says is very important further, that therefore school mathematics should encourage proof as a systematic way of argumentation. The aim should be to develop arguments, evaluate arguments, make and investigate conjectures, and understand that there are various methods of reasoning. And one of the great the features of the tool, a tool like GeoGebra or any dynamic geometry software, but specifically GeoGebra, is that all this can be made possible by designing the right kind of tasks for exploration by students. So there are many research studies, the landscape of research studies in mathematics education, and the research studies on the use of technology in mathematics education is quite dense. But one of the landmark studies was that by Kathleen Hyde way back in '88, when she said, digital technology can be used as a lever to reorganize a course using a concept-first approach. So there were studies done where, university first-year students were taught calculus using the then existing technology, and the focus was on them building the concepts, and procedural aspects were left towards the end of the course. And studies and the data showed that, there was no compromise on their learning and on developing procedural methods and hands-on skills. And another important aspect of technology is the cognitive aspect, which says that, there are two metaphors used, that technology can be an amplifier and a reorganizer. So amplifier means that the range of possibilities available to us when we use technology for teaching or exploration is much more. And we can, at very quick, high speed, and accuracy, we can generate a set of graphs, or you can generate a table of values. And basically you can outsource some of the computation to the tool, and you can focus on insights and concepts. And also it's a reorganizer because, it changes the way we sequence our lessons. We need to change the way we sequence our lessons, because the focus would be on looking for patterns, identifying invariances, making and testing conjectures, and so on. Now, if everybody probably knows this, but I'll just go over this in any case, that in a dynamic geometry software, figures are dynamic. So I have screenshots here. So these are not dynamic. I don't want to toggle too much between this and the GeoGebra screen, but off and on I'll do that. So once you create a figure, the figure is dynamic. It can be manipulated by dragging. And parts of a figure in the algebra view, so in the graphics view, if I draw a triangle and mark the angles, and in the when I drag the vertex, in the algebra view, the different aspects of the figure change. So some things change and some things do not change. So there is, if I measure the angles, interior angle sum, then that will be constant at 180 degrees. So children can observe properties which remain invariant and those which vary. And this helps them to verify properties and make conjectures. And researchers have used the term a micro world for a tool like a dynamic geometry software. So, of course, I am going to take examples which are more typically accessible to school children, middle school upwards to maybe grade 12. So, some of the features we already know in a dynamic geometry software like GeoGebra are the drag mode. The drag mode itself becomes a tool when an element of a diagram is dragged with the mouse, the diagram is modified while all its geometrical relations are used in its construction are preserved. Then there's a trace tool which can trace the path of a moving point. You can create a locus. You can hide and hide features, which really is helpful. And this is so in a paper pencil environment, these features are not accessible. And therefore, any tool like this will definitely have a great advantage over paper pencil constructions. So now the important questions to ask are, how can mathematical concepts be experienced differently in a dynamic geometry software than on paper pencil mode? And this is of, I think, research interest to mathematics educators. How are geometrical explorations in a DGS different from that of ruler and compass on paper? But how do students perceive these differences more importantly? How do they perceive such geometrical objects? What are their thoughts? What are the nature of conjectures made by them? How do they create explanations, argumentation, justification, and so on? These are more pedagogical aspects that we need to focus on when we use any technology tool, because most tools have tremendous possibilities, but we also need to see how students can access them and how their learning and their mathematical thinking develops in such a context. So one of the main advantages, of course, such a tool has, as you can see on the screen, it's a static picture. But if you want a student to visualize the limit of a function, you can create a simple screen where you input certain functions and you ask them one by one to graph the function. So suppose I want them to explore the limit intuitively explore the limit of this function, this rational expression as x approaches 2. So in the graphical mode, I can drag a point A along the graph and see the values of A as it is changing. And in a spreadsheet, I can numerically see the same thing. So though this function is not defined at 2, according to what the spreadsheet is revealing, but as x approaches 2 on either side, the left hand and right hand limit both seem to be approaching something like 2.25. And it can be verified using the limit command. One can simultaneously open a CAS window and verify the same using the limit command. So multiple representations, that is using symbolic mode, the graphic mode, and the numeric all together, they come together to help the student visualize the idea or the concept. So many such things can be done in calculus, and I'm sure there have been some interesting workshops related to calculus prior to this GeoGebra conference also. Now I come to little younger children, and I will share the results of a study which was done with grade 7 children in India and in Sweden. And in fact, you have just heard Thomas Lingerfeld in a previous session. So Thomas and I collaborated on certain studies and the research, and the study was such that Indian students, some Indians, grade 7 students in Mumbai were attempting certain tasks, and at the same time, students of grade 7 in Sweden were also attempting the similar tasks who had similar level of ability. And we tried to give them the same task and see how do they respond to these tasks. And these children had no exposure to GeoGebra prior to this study. So first task which was given to them was to construct a square. They knew that they were just familiarized with the basic tools of GeoGebra, and then they were asked to construct a square. So what they did was they drew 4 points and marked them and just created a square. Now by manual adjustment, so they manually adjusted and tried to make sure that all 4 sides are equal and so on. But when they dragged a vertex, they saw that it's no longer a square. So this is not a robust construction. It's a drawing, but it loses the property of a square the moment you drag a vertex. Then some children, in this study, there was minimum intervention on the part of the teacher and the researcher. So children themselves had discovered that there is a regular polygon tool, and they use this to just draw a square, and others started telling them that's cheating because GeoGebra is doing it itself and you are not really constructing the square. But by using the regular polygon tool and dragging the vertex, they could see that the size of the square can be enlarged, it can be shrunk. But the main thing, that fact that it's a square, it remains. So the equality of the sides and the angles remain 90 degrees. And then they actually were asked to use the construction tools of GeoGebra, in which they created a line segment, drew circles to ensure that all the four sides are equal and so on. And when this square was constructed and they removed or hid the circles and the additional lines, they experienced a square which was robust, a robust construction. So students learned the difference between a drawing and a construction, and they experienced varying appearances of a square in a visual dynamic way. So 3 ways were done, and they started understanding the difference between what is a simple drawing and what is a robust construction. So it is meaningful to ask students to produce constructions rather than drawings. And this helps to understand and improve their understanding of formal definitions of and relationships among geometric objects. So a meaningful task could be construct a rhombus and explain why it is a rhombus and how is it different from constructing a square. Or can you construct a rectangle and drag it so that it becomes a square? So how can this be used to explain that all squares are rectangles, but all rectangles are not squares? So hierarchical inclusion, of quadrilaterals, let us say. So for grade 7 middle school children, these kind of tasks help to enhance a lot of dialogue and discussion in the class among the children, by which they themselves seem to be abstracting these ideas and concepts. Children were asked to construct a regular hexagon in at least two different ways, and here using GeoGebra tools. And this is what they did. One group of students, there were many responses, but two of the common responses were that they constructed an equilateral triangle first and used the reflect about line option to keep reflecting that triangle about different line segments to complete the hexagon. So here they use the property that a hexagon consists of 6 equilateral triangles. In another group of students drew a line segment, and using the angle of fixed measure option, they drew 120 degrees on both the sides, and then they kept drawing 120 degree angles and completed the hexagon. So here they used the property of the interior angle of a hexagon. So multiple responses are possible, and children start exploring on their own and justifying also why they are doing that. So that is a very interesting aspect which naturally comes up when one is in the presence of such a tool. Moreover, a constructed figure, as we know, is not a in GeoGebra is not a static diagram. It is a variable figure that preserves invariant or defining properties. And then the drag test. So by dragging, suppose I construct a robust hexagon, I should drag one of the vertices and see that the figure doesn't get messed up upon dragging. That means its inherent properties should remain invariant. So students can explore multiple approaches of construction. Now the drag tool itself is something which is, the dragging feature of GeoGebra actually is a tool in itself, because it is possible to discern critical invariant properties under a continuous variation. So as you are animating, that means as you are dragging the figure, it is smoothly transitioning, and in a short drag, multiple triangles, for example, if you create a triangle, you can experience multiple appearances of a triangle by dragging, and you can see that the angle measures are changing, the side lengths are changing, but the visual consistency of the fact that the sum of the 3 interior angles is 180 degrees, it comes to the fore, it kind of emerges, and that can become a conjecture by students. Here, of course, we have to be careful, because sometimes students make a conjecture and think that that itself is the proof, but that is not the proof, and slowly they have to be sensitized to that fact. And with another study, I would like to show how this happened. Visual representations are, of course, very wonderful. So, there's a lot of study in the literature which says that can a visual representation be considered akin to a proof? Well, certainly not, but a visual representation can motivate the need or desire for proof. So if you can drag this vertex and show that all the exterior angles, sum of the exterior angles of this polygon is equal to 360 degrees, this should be a motivation to allow the student to think how we can actually go about proving it. And when we want to show more important concepts in calculus, like the area under a curve, using sliders, the number of rectangles can be varied so as to visualize the lower sum and upper sum. So in this case, maybe I'll just quickly like to take you to this. Is the GeoGebra screen visible? So
yes.
Okay. So if I take the lower sum, and here this is a cubic function, and n is the number of rectangles which we will use to approximate the area under this curve from A to B. So as I increase the number of rectangles, I see that the rectangles are increasing and it is covering up the area under the curve from below the curve. So in school, when this concept is taught without technology, you know, one had to draw a lot of figures and it was very complicated. It was not really possible to do it effectively. So by the time there are 50 rectangles, it fairly covers, but there are of course still some gaps. And as you can see, the value of the lower sum here is 5.84 by the time it is 50 rectangles. And now if you hide the lower sum and you mark the upper sum, so now the single rectangle is much more than the area under the curve. But as you increase this, it approaches the curve and from above. So then the lower sum, it approaches from below, and from the upper sum, it approaches from above. And after 50 rectangles, there's a gap between the lower sum and upper sum. But if you increase the number of rectangles to say 200 or more, you will obviously see that gap reduces. But there's also the trapezoidal rule where you can approximate the area under the curve using trapezoids. And that, of course, converges to the area sooner or faster than the rectangles. And these kind of things, creating this kind of an animation would hardly take not even 2 minutes. So this is the power of a tool like this. Even if you don't know a high-level programming on this tool, but using the basic features, you can do enough to create an aha experience in the class. Okay, so coming back to the slide, I would just briefly like to mention the theory of variation. One of the learning theories, because it is said that something like GeoGebra is rooted in variation in its very design, which means let us pose a very simple task. Let's suppose there are two arbitrary points A and B on the screen, and you have to construct a circle passing through A and B. So how would we go about it? So the first thing is to locate the center C of the circle on which A and B will lie. Because we want that point, we want a circle through A and B, so we want the center of that. We want to identify the center of that circle. If there are 2 points A and B, and let's say these are the 2 points, and we take the midpoint of A and B. The point C is, then AB becomes the diameter of the circle, and you can easily construct the circle. And of course, if you drag one of these points A or B, the size of the circle reduces, can be enlarged, can be decreased. But what is happening is that you are getting different circles, different positions of C. So C is dependent on A and B, so you can think of C as a function which is dependent on the independent points A and B. So by dragging A or B, we would get the dimensions of variation. But what would happen if C is not the midpoint of A and B? So if A and B are not the endpoints of the diameter, how do we find C and draw the circle? So this is something you can ask very young children and see how they respond. So what we need to do is we need to locate point C which satisfy the condition that CA is equal to CB, so that CA or CB becomes the radius, and then you can draw the circle. So by dragging, which is also called wandering dragging, by wandering dragging means you kind of drag your cursor in such a way that you try to look for points such that CA is equal to CB. This helps us to locate such points, and such points will produce circles. So there will be a certain kind of points which will produce circles on which A and B will lie, and there will be certain points which will not produce circles. So the positions of C that are circle producing and those which are not bring about a contrasting experience, and this contrast helps one to observe, make the observation. So for example, here, if A and B are here, then C could be here, C could be little low, or C could be above. But all these points see a circle producing. I mean, if you now create a circle CA, A and B will definitely lie on the circle. So it is important to have contrast, because in order to experience something, a person must experience something else to compare it with. The next is generalization. So in order to understand a concept, we must experience varying appearances of that concept. How do we visualize varying appearances of this invariant length, CA is equal to CB? So what we do is we keep on dragging the point C and look for positions so that CA will be equal to CB. And then we find that we can actually trace the path of this moving point. And using the trace option, we can see this. But this traced path, also referred to as the locus of validity, is nothing but the perpendicular bisector of A and B. So, this is the any point on this line will be circle producing and will produce a circle which passes through. If the center is on this line, it will produce a circle which passes through A and B. So finally, when we are dragging, everything, all points cannot be varied. So it may be better to fix certain things, so that we must decide what should be in the foreground and what should be in the background when we are dragging something in a dragging episode. So maybe for this problem, we simply fix the positions of A and B, and we only try to vary C and see what is happening. So that is called separation. And finally, fusion. These are the 4 functions of variation, the theory of variation. If there are certain critical aspects of a concept that a learner has to take into consideration, they must all be experienced simultaneously. So simultaneous experiencing means that the constraint that CA has to be equal to CB, the path or the locus of validity, that is the path traced by the point C, and the circle passing through A and B, if they are all experienced simultaneously, then truly will the learner experience variation and will be able to learn or understand the concept through the theory of variation. Now, this plays a significant role in most conjecture making studies and episodes. Now, in grade 7, the 7th grade students that I talked about, they were given this task, which is also a well-known task actually, where they were to draw an quadrilateral, any quadrilateral, join the midpoints of the 4 sides, and make a conjecture about what is the inner quadrilateral. So they use the construction tools of GeoGebra and tried to make conjectures. They dragged the outer quadrilateral so that it became different kinds of quadrilaterals. Somebody said my inner quadrilateral EFGH is a rhombus. Somebody said it's a parallelogram. Somebody said it's a square. So there were different responses by the children initially, and then some kids actually, which normally would not have come up in a traditional paper pencil episode of learning, was perhaps that they dragged one of the vertices and they made the quadrilateral look like a concave quadrilateral. And then they said, then the other children started commenting, but what you've done, ABCD is not a quadrilateral anymore. So then they argued why it is not or why it is still a quadrilateral. But of course, it's a different kind of quadrilateral. And here they started saying, still it is a parallelogram, or in this case, a rectangle. But although the side lengths are coming outside the quadrilateral, but still it is a parallelogram. So initially there was a lot of debate as to what the inner shape should be, but finally there were a lot of, so that was a whole lengthy study where they were asked, whenever a child made a conjecture that this inner quadrilateral is so and so quadrilateral, they were asked for a proof. So in this case, the students worked in pairs, and in each pair, one student sketched. So they were sitting in front of the computer terminal, and one student sketched with the construction with paper and pencil, and the other partner was using GeoGebra, and then they switched after some time. So in this peer collaboration, the students were learning and practicing both communication and reasoning. So the dialogues that they spoke to each other was interesting. And they moved. It's not that they were only focused on the technology. They moved back and forth between GeoGebra and paper and pencil. And most importantly, they asked what if questions. What if I drag this and make the outer quadrilateral a rectangle? Then what happens to the inner quadrilateral? what if the outer quadrilateral itself is a parallelogram? Then what happens to the inner quadrilateral? So these kind of questions started coming up. And at the end, students were asked for feedback, and many of them said that, their paper pencil, they claimed that their paper pencil constructions were less accurate than the GeoGebra constructions. And eventually, almost more than 2/3 of the students who participated in the study, as I said, it was an Indo-Swedish kind of a study. They were all able to make the conjecture that the midpoint quadrilateral EFGH is always a parallelogram. But the type of parallelogram depends on the outer quadrilateral ABCD. So this was an important statement made by the children. But of course, they had to be scaffolded so that they could come up with the proof. And so as far as the inner quadrilateral was concerned, students started thinking about their own ways of proving using the tools of GeoGebra. So for example, they said that, we can show that we already see from the algebra view that opposite sides are equal. But can opposite sides be shown to be parallel? So one child said that, look, if I want to show that EH is parallel to FG, then I will ask GeoGebra I'll use the parallel line tool of GeoGebra to draw a line through E parallel to FG. And if it coincides with HE, then surely HE is parallel to GH. So this kind of suggestions started coming from students. These kind of arguments started coming from students. Also, the researchers asked a few questions like, is a rectangle a parallelogram, or is a square or a rhombus a parallelogram? And when children were claiming that their inner quadrilateral was a particular kind of quadrilateral, so all the properties of quadrilaterals were automatically revisited. So students, whenever by this time they reached this stage, they were kind of looking for reasoning and proof. It was not that they were just satisfied with the fact that it looks like a parallelogram. They wanted to give arguments as to why it is a parallelogram. And how did the transition to proof? So soon the concept of slope was also introduced. These were only grade 7 children. So they were the concept of slope was taken up to show that, opposite sides have the same slope. And so it was a new concept they encountered. And the midpoint theorem was also introduced. And finally, the midpoint theorem was used to justify that, like in this case, if the dotted line is a diagonal of the outer quadrilateral, then by the midpoint theorem, HE is equal to half of BD and parallel to it, and similarly for FG and so on. So they used the midpoint theorem to prove, and they of course wrote their argumentation on worksheets which were given to them, and these were used for our research and records. And while transitioning to proof, the students had to also make a conjecture about the area of the parallelogram with regard to the quadrilateral ABCD. So what is the area of this inner quadrilateral with respect to the outer one? And from the algebra view, they could see that it is almost equal to half. But then again, this was a conjecture and they had to prove it. So they actually proved it by the method used by them was quite interesting, because the diagonal BD. Mute yourself. So the diagonal BD of the outer quadrilateral divides the inner quadrilateral into two parts. So the students suggested that why don't we show that this part, the upper part, is half of one triangle and the lower part is half of the other triangle in area, and therefore the combined part would be half of this. So these kind of suggestions, a strategy of proof was kind of suggested by students with scaffolding, of course, wherever required. And they actually, this is a snapshot of the kind of reasoning that they wrote to prove their claims. Then, there was a series of inner quadrilaterals which were created, and there was a series of areas which was generated, and they continued to make conjectures. So it appeared that even though it was not within planned so much in the study, the series of inner quadrilaterals, the students wanted to explore these on their own. So by the end of it, so in the initial stage, students focused more on description rather than explanations and justification. But in the middle stage of the study, it was found that the children were influenced, their language became more mathematically precise, and it was influenced by the terminology of GeoGebra. Like they would say things like this is a draggable square, or this is a draggable rectangle, or whatever. And at the end, their explanations became more mathematical. Actually, when they were writing it in the form of proof on their worksheets, and at that time they were thinking logically and they were not really using GeoGebra as such. So there was definitely an evidence of a shift in their thinking. And older children, there was another study done with a group of older children of grade 9, where they had to construct the centers of a triangle, the Euler's line, as we all know, this is a very well-known task. Here, this is a snapshot of what was really done. So they constructed the circumcenter, centroid, and the orthocenter of a triangle, and saw that these actually lie on a straight line. So by dragging, you can see that it actually lies in a straight line. So let me see if it is possible for me to do that. Okay, can you see the GeoGebra, this screen?
Yeah. Please go ahead.
Yeah, so basically here they could see that by dragging, the red line is the Euler's line, the circumcenter, centroid, and orthocenter H lie on the same line. But when it had to be proved, so when they proved, they could see the line of proof is as follows, that you have to show that you assume that you first construct the circumcenter, then you construct the centroid, and you extend the line OG to twice its length to a point, let's say H. We have to show that H is actually the orthocenter of the triangle. So that's a line of proof. So when these two triangles were created, students argued that these two triangles are similar because AG is twice of GD because G is the centroid, and HG is twice of OG by construction. And these two sides are vertical, these two angles are vertically opposite. So by that argument, one could easily see that these two triangles are similar. And even by dragging, the similarity is not lost. So if the two triangles are similar, then this angle on top here, that is HAG, is equal to ODG. And this ensures that AH, the line AH is parallel to OD, but OD is perpendicular to BC because OD is the perpendicular bisector, and therefore AH must also be perpendicular to BC, and therefore AH is actually a part of an altitude. And using such arguments, you can show that H actually is the orthocenter. And that is a classical way of proving that the three centers are actually collinear. So the notion of proving is quite different from the construction process, but using this, they could actually, it was more like a dynamic figure in which they could see certain things happening and similarity being maintained and so on. So with this, I'll just close this. And the final study that I would like to briefly mention is the famous 9-point circle or the Euler's circle. In this case, as we know that, in a triangle, there are 9 points which always lie on a circle, or a circle passes through 9 specific points of the triangle. So let me again try and see if I can show you this. So here is a triangle, and which are the 9 points? So let me see. The 9 points are the midpoints of the 3 sides. So D, E, F are the midpoints of the 3 sides of the triangle. Then I and J and K are the feet of the altitudes. So that means if I draw an altitude from A to BC, I is the foot of the altitude. So each side has a foot of the altitude. And H is the orthocenter of the triangle. So if I were to connect H to the 3 sides, 3 vertices, ABC, L, M, and N are actually the midpoints of these lines, AH, BH, and CH, where H is the orthocenter. So if I drag, I can see that, so children constructed these points, and then they said, these points seem to be swimming around the triangle. So somebody says, oh, let's see what happens, if it becomes a right angle triangle. And what happens if it becomes an obtuse angle triangle? What happens to these 9 points? So everybody said, look, we can't say about the obtuse case and the right case, but in an acute angle triangle, definitely it looks as if they would lie on a circle. So that was very interesting. And then, they had to now really establish how these 9 points actually lie on a circle. So the line of proof was as follows. I'll quickly try to demonstrate this and just see if that's possible. So first, one could take 4 of these 9 points. So let's take F, E, N, and M. And one could try and show that F, E, and M is indeed a rectangle. It looks like a rectangle. That's what children said. But how do you prove? Then others started telling them, but you can't just say it looks like it. You have to actually come up with the reasoning why it is so. So first thing was that, FE is parallel to BC because by midpoint theorem. And MN is also parallel to BC by the midpoint theorem, because in the case of FE, it is the midpoint line joining the midpoints of the big triangle. But in the MN is the line joining the midpoints of the smaller triangle, HBC, and so on. So using midpoint theorem, they could show that the opposite sides are equal and parallel, and therefore it's a parallelogram. But they also established that FM is actually perpendicular to MN. And one can see why this is so, because FN is actually parallel to AH, which is the altitude, and so on. So this becomes a rectangle, and therefore it is a cyclic quadrilateral. So we can find a circle for which F, M, and E lie on that circle. Then you can take another 4 points. Let's take the green one. By similar arguments, we can show that the green figure, that is LNDF, is also a rectangle. And both these rectangles have a common diagonal, FN. And the center, if I were to take the center of that common diagonal FN, that would actually lead me to the 9-point circle. So this is the 9-point circle. Of course, you have to establish the 3 other remaining points are also on that circle, and that can be easily done through some arguments. So this was, and what happens, when it becomes an acute angle triangle.
Janaki,
yes.
You have 5 minutes more to.
Yeah, I'm concluding, sir.
Okay.
Just 1-2 more slides and I'm concluding. So the line of proof was, as I showed you, the first step was the construction of the points, then was to see that there is a circle which exists. And in the acute angle case, it was very obvious. In the right angle case, children got very excited because they could not see some of the points. So they started saying some points have come on top of others. They have coincided. So why have they coincided? So this was called to be referred to as a degenerate case. And then if you take the obtuse angle, then it kind of comes outside the triangle. So the contrasting experience of the varying and the invariant. So they could see that the existence of the circle is invariant, whereas the triangle itself is varying. And so there were many interesting arguments posed by students as to, for example, in the right angle case, why some points are coinciding, why others are not, and so on. And this was the line of proof which I already have indicated to you, this, which you can use these 2 rectangles to show that they have a common diagonal, and that common diagonal happens to be the diameter of the 9-point circle. And students' justifications were very interesting as they started, the teacher did not have to ask for arguments. The students were themselves coming up with the arguments. And finally, it can also be shown that the feet of the altitudes I, J, K also lie on the same circle, because in this particular case of the triangle, LID is actually a right angle. And by the opposite, by the converse of the theorem that angle in a semicircle is 90 degrees, we can show that this point also lies on the circle. So in conclusion, I would just quickly say that, in such experiments, GeoGebra or something like GeoGebra would be an exploratory tool, like a mathematical investigation assistant, kind of for the student, giving them control over what they are learning, but giving them freedom at the same time. And it is certainly a non-traditional way of understanding mathematical concepts. The dragging tool initially is externally oriented and is used for verifying conjectures, but with time, it changes its functionality and becomes an internally oriented tool. So, internally you can imagine animations happening once you are used to GeoGebra or something like a tool like this for some time. Definitely, it's a computational tool. It helps to facilitate the computational process by quickly generating figures. So technical work is, students are kind of relieved from the technical work, but they can focus on observations. And certainly in these experiments and other studies have shown that, you know, such tool can definitely be an amplifier and reorganizer. And so with this, I'd like to conclude, and I hope teachers feel that there is some merit in using these tools even for young children in the classrooms.
Thank you, Janaki. That was very informative, and I think mathematical investigations must be a part of classroom experience, and that is how they are going to make their own proofs. And after following up with these conjectures, the teachers can actually take it up in the classroom and explain the concept of proof. First, you have to build the conjecture, then use this dynamic platform to verify all the geometric results virtually. Then once the students get hold of the concept, then the proof can be done much more. I think the concept of proof will become much strengthened in the minds of the students. And after all, this goes with the fact that children construct knowledge by themselves. So all these activities will help students to construct knowledge by themselves. So participants, do you have any questions? Any participant would like to ask any question?
There's somebody who says, can you explain the limit of a function? I could share some videos which I've prepared for calculus. Maybe I can share that link, Revati, later on.
That will be nice.
Yes. Yes, but it will take some time to create that and show right now. But yeah.
And also, because we have already mentioned that there is a Makkah for applets, there is called GeoGebra.org.
Yes.
And there is a search engine there. If you enter the word limits, you will find not only of Janaki's applets, but many more also. So see whichever you like, whichever you can use in your classroom and so on. Or you may modify them, actually download and modify according to your needs. That is the beauty of those applets, because it's open source and nobody minds. But always it's good to give credit that original modified by so and so. That will be nice. But even if you don't do that, nobody minds that. I just want to add one thing more to the work that you have been doing. You see, it's not only it excites the mind of young children that they are doing some kind of explorations and playing around with mathematical objects. In fact, when they discover a theorem or discover a conjecture, they are making mathematics as their own.
Yes, yes.
That is very important. When a teacher is teaching in a class, he or she is teaching something that is given in the book. That is not created by the teacher or created by the students. They know that this is given by somebody else, probably who wrote the book. Yes. But once they discover something, right, even if it is in the book, it becomes their own knowledge. It becomes something their own discovery. And the pleasure of discovering something stays lifelong with yourself. Not only mathematics, discovering anything in life stays with you. So that is the feeling that we should try to give our students. That's my feeling about explorations and investigations.
Yes.
Anybody else has a? Yeah, people are appreciating hands-on activity will always help teaching learning process. That's good, and practice in your classroom. So Revati, would you like to conclude the function by as a chair?
Yeah. See, Janaki has opened the possible opportunities that can be taken to the classroom. So I think teachers handling these classes should, I think, give enough opportunities for students where they can do these kind of every topic when they prepare the lesson plan should be supported by an well planned activity for students where they explore these concepts and come up with a conjecture. And sir, as you rightly mentioned, make mathematics their own. So whatever they are creating, it is their own creation. So as you rightly mentioned, it will stay with them forever, and that would help them in the path of mathematics, tracing the path of in the curve, in the educational curve, the learning curve. This will be at a great value. So that is what I would like to say, and that is what in many schools where the teachers are using GeoGebra are doing. So they do have a mathematics activity period. So I request all teachers who are participating in this conference not to just stop by just attending these talks, but to actually take it to the classroom. So you will have to have classes, GeoGebra classes. That is what I think is needed now. So 1 hour a week should be introduced in the timetable, in the curriculum for GeoGebra, where the students explore and investigate concepts, and teachers act as facilitators, not just people who just lecture in the classroom. I think that has to change. The role of teacher has to change. The teacher has to be only a facilitator who facilitates the learning, which is possible with all such activities.
And which I may add is more challenging and interesting. Being facilitator, because there are diverse kinds of thinking which emerge in the classroom.
Exactly.
So managing that, the teacher's role becomes more interesting and challenging than just
Just like you have the static graph, and what GeoGebra makes it, no more static, right? So that is the way the role of the teacher also will change. From being standing in front of a classroom and just addressing them and doing things on the board, to being just active, doing just the role of a facilitator, just spark off the questions, spark off the investigation, spark off the thinking in students, and then you facilitate the whole process. Then the dynamism of the whole classroom will change. So there will be group learning, there will be collaborative work. So if you look at it, if you look at the learning that is coming out of a classroom, that will be phenomenal. I think that there is such a scope for phenomenal growth in learning with such ideas. So I hope all the participants, so on behalf of all the participants, thank you, Janaki, for being here today and sharing your valuable inputs to take it to the mathematics, to the classroom. Now it is their responsibility to take it to the classrooms. Thank you, sir, and thank you, Janaki.
Professor Rana, thank you.
Thank you, Janaki, for taking time, and thank you, Revati, for chairing the session. Thank you very much.
My pleasure. Thank you.
So we formally close the present session. Before Soumya has anything to say about the general instructions or something, we meet tomorrow at 10 o'clock about hidden treasures of mathematics using GeoGebra. That is the first talk. Please, Soumya, would you like to say something as a concluding or something?
Yeah, so maybe we can have another feedback poll from participants.
Yeah, please.
I have already opened it.
Yeah, so
so the Zoom link for tomorrow would be different. It's already communicated to all the participants.
So
email.
Joining link for tomorrow is different for each day. So tomorrow it will be different, but it is already communicated to you beforehand. So please be careful while joining tomorrow for the thing. And of course, there will be a concluding function at 4 o'clock tomorrow, 4:10. So be ready for your firing questions, firing criticism or anything that you want to say, because this is the first time we are holding this conference, that too virtually. So your feedback will be important, not only for each session, but overall feedback tomorrow in the concluding function will be important. So do come in the evening, but I would say please go through all the sessions anyway, because as a convener, because afternoon there are teacher presentations from 12 o'clock onwards, how teachers are using it actually in their classroom. They are presenting. So it will be nice. Yeah. So thank you, Janaki and Revati once again.
Yeah, it was fun meeting both of you.
Yes.
Such a pleasure.
Okay. It's a pleasure meeting you all.
Bye.
Yeah. Bye. Take care.
Bye.
Soumya, is it over?
Yeah, it's almost over. So we can close.
Yeah, we can close. So bye.
Yeah.